Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. We look up on a clear night and see thousands of tiny lights sprinkled across the sky. From ancient times to the present, people have been captivated by the stars. They have inspired wonder, guided travelers, and sparked countless myths and legends. Humans imagined patterns in them and told stories about gods, heroes, and animals in the heavens. We use the stars to navigate oceans and to mark the seasons. But what are these brilliant pinpricks of light really? Stars are giant, luminous balls of plasma, held together by their own gravity and powered by nuclear fusion at their cores. In simple terms, a star is a colossal nuclear furnace in space, constantly fusing lighter elements into heavier ones and releasing tremendous energy as light and heat. They seem eternal and unchanging to us, but in reality, stars are born, they age, and they die, undergoing dramatic changes over millions or billions of years. Our Sun is one such star. In fact, it's the only star close enough for us to feel its warmth and light directly. And it's just one among an uncountable multitude of stars in the universe, each with its own story. Now, imagine journeying into a vast cosmic cloud far out in space, where new stars are born. These regions are called nebulae, enormous, diffuse nurseries of gas and dust, sprinkled throughout the galaxies. They are the cradles of star formation. If you could float inside one, you might see faint, ghostly glows and dark, opaque patches where starlight from outside is blocked. The famous pillars of creation. Photograph of the Eagle Nebula, for instance, shows towering columns of gas and dust rising like mountainous spires. Within those cold, shadowy pillars, new stars are slowly taking shape. The Great Orion Nebula, visible as a faint smudge in Orion's sword, is one such stellar nursery. A cavern of gas and dust over 20 light-years wide, where thousands of baby stars are forming. Here, in the cold, dark depths of a nebula, the story of a star begins. A slight nudge, perhaps the shockwave from a distant supernova or a random density fluctuation, causes parts of the cloud to begin collapsing under their own gravity. Over thousands to millions of years, a portion of the nebula's gas gathers more and more mass, pulling in surrounding material. As this pocket of gas shrinks, it grows denser and hotter, and it starts to spin faster. Eventually, it forms a growing ball of gas known as a protostar, a baby star that's still gathering mass. Surrounding it, a flat disk of gas and dust often forms, whirling around the protostar. Protostars also often fire out bipolar jets, narrow beams of gas blasting out from their north and south poles. These high-speed jets can plow through the surrounding nebula, creating glowing shockwaves and carving cavities in the cloud. The protostar at the center continues to contract and heat up as gravity relentlessly squeezes it. Deep in the core of this protostar, temperatures climb into the millions of degrees. The gas is mostly hydrogen, the simplest and lightest element. When the core temperature reaches roughly 15 million degrees Celsius, something miraculous happens. Ignition. Hydrogen nuclei begin to fuse together to form helium, unleashing a tremendous amount of energy. This is the moment a star is truly born. The protostar has become a full-fledged star, blazing with its own light. The once dark core suddenly glows brilliantly, and the outward pressure of this new energy release halts the gas collapse. The infant star turns on, so to speak, and starts shining. The surrounding cocoon of leftover gas and dust gets blown away by the fierce stellar winds and radiation now pouring from the newborn star. The star stabilizes, no longer contracting, as a balance is struck. It has entered the long, stable phase of its life, known as the main sequence. Often, stars do not form alone. Many newborn stars come in groups called star clusters. Our Sun likely formed in a cluster with several sibling stars. which have since drifted away. Once nuclear fusion starts in the core, a star finds an equilibrium. Outward pressure from the fusion energy balances the inward pull of gravity, and the star stops shrinking. It becomes stable, neither collapsing nor exploding, steadily glowing. The star will remain in this state, fusing hydrogen in its core for the vast majority of its lifetime. It's as if the stellar engine is idling at a steady rate. This newfound stability allows the star to shine consistently for a very long time. Millions, even billions of years will pass with the star in this tranquil main sequence phase. Our Sun is in fact in this phase right now and has been for about 4.6 billion years. This stability is fortunate for us. It means the Sun's energy has been steady enough to allow life to develop on Earth and will continue for eons more. If our Sun were a short-lived massive star, life as we know it might never have had the chance to arise in the brief stellar lifetime. Main, sequence stars like the Sun quietly convert hydrogen to helium, radiating energy into space and providing warmth and light to any orbiting planets. In this main sequence stage, a star shines by nuclear fusion, fusing hydrogen atoms into helium in its core, and in doing so, it releases an absolutely colossal amount of energy. To give a sense of scale, our Sun fuses about 600 million tons of hydrogen every second, turning it into about 596 million tons of helium. The missing mass, roughly 4 million tons per second, is converted to pure energy according to Einstein's famous equation E=mc². 4 million tons of matter turned into energy every single second. This energy then radiates outward from the core, through the Sun's layers, and eventually into space as heat and light. The numbers are mind-boggling. The Sun's energy output each second is about 3.8 × 10^26 watts, a figure almost impossible to imagine. To put it in human terms, the power the Sun releases every second is equivalent to the energy from billions of nuclear bombs exploding at once. Yet this gargantuan output has been running continuously for billions of years, and will continue for billions more. It's sobering to realize that for most of human history, the source of the Sun's power was a mystery. Only in the 20th century did scientists like Arthur Eddington and Hans Bethe figure out that nuclear fusion is what makes the stars shine. Millions of such stars fill our galaxy, each a massive energy source blazing in space. Not all stars are like our Sun, however. Stars come in a stunning variety of sizes, colors, and luminosities. Some are far bigger and hotter than the Sun, shining blue, white, and piercingly bright. Others are smaller and cooler, glowing a faint red. The color of a star is a clue to its surface temperature. Hotter stars emit more blue, white light. Cooler stars more red, orange light. For example, in the constellation Orion, you can spot a contrast between the supergiant star Betelgeuse, which shines with a reddish hue, and Rigel, which gleams bluish-white. In general, a blue star might be tens of thousands of degrees at its surface, while a red star might be only a few thousand degrees. These differences correspond to spectral classes. Another example, the star Sirius, the brightest star in Earth's night sky, is about twice the Sun's mass and has a surface temperature of around 9,400 K, giving it a white-blue sparkle. On the other hand, our Sun is yellow, white, and a typical small red dwarf star would look deep red to our eyes. The vast majority of stars in our galaxy are actually small, cool red dwarfs. Perhaps 70–80% of all stars fall into this category. These red dwarfs are so dim that not a single one is visible without a telescope. In fact, the smallest true star ever measured is only slightly larger than the planet Saturn. With just about 8% of the Sun's mass, it barely manages to sustain fusion. Were it any smaller, it would fail to ignite and become a failed star, known as a brown dwarf. By contrast, most of the stars we see sparkling in the night sky are the larger,
more luminous types that, while much rarer, shine hundreds or thousands of times brighter than red dwarfs and can be seen across great distances. If you stood on a hypothetical planet orbiting a red dwarf, the star might hang in a dim red sky, casting an eerie dusk, like light even at noon. By contrast, a planet around a hot blue-white star would be flooded with a stark, bluish illumination and intense ultraviolet rays. Size and mass have a profound effect on a star's fate. In general, the more massive a star, the hotter and brighter it burns, and the shorter its life. A star 10 times more massive than the Sun might emit thousands of times more energy, blazing a brilliant blue-white, but it will use up its fuel at an unsustainable rate. It's the difference between a gas, guzzling sports car and an economy car. The massive star burns through its fuel quickly, while a small star is extremely fuel efficient. Massive stars live fast and die young in a cosmic sense. Such a star might last only a few million years before it exhausts its core fuel. In contrast, a tiny red dwarf sips its hydrogen fuel so slowly that it can continue burning for hundreds of billions or even trillions of years. To put it in perspective, the universe itself is about 13.8 billion years old, so no red dwarf has had time to even come close to dying yet. Our Sun lies somewhere in the middle of the mass range. It's a G-type yellow dwarf, not exceptionally massive or small. It will have a total lifetime of roughly 10 billion years, moderately long by stellar standards. So far, the Sun has been shining for about 4.6 billion years, and it has about 5 billion to go before it starts to run out of core hydrogen. Because of these lifespan differences, no red dwarf star has ever died in the history of the universe. The universe simply hasn't been around long enough for the smallest, slowest, burning stars to use up their fuel. Even the oldest red dwarfs, born shortly after the Big Bang, are still shining today and will keep on shining for trillions of years to come. By the far distant future, long after bigger stars like the Sun have died, red dwarfs will be the last stars remaining, quietly glowing red in a fading universe. On the other end of the spectrum, many massive stars have lived and died in that same time, blazing through their fuel in a few million years and ending in catastrophic explosions. In a sense, the cosmos has a way of favoring the slow and steady when it comes to longevity. Eventually, even the most long-lived star will run low on fuel. When a star has fused most of the hydrogen in its core into helium, it starts to leave the stable phase of its life. The delicate balance that maintained the star for so long begins to falter. With less nuclear energy being produced in the core, the outward pressure that held the star up drops. The core, now largely helium, begins to contract under gravity since nothing is pushing back as strongly. And when the core of the star contracts, surprising things happen in the layers around it. The contracting core heats up a lot. This intense heat radiates into the surrounding shell of hydrogen that wasn't previously hot enough to fuse. Now that shell of hydrogen does begin fusion. So hydrogen fusion essentially migrates from the core to a shell around the core. Meanwhile, the helium core will eventually get hot enough to ignite a new kind of fusion. It will start fusing helium into carbon. The star's internal structure rearranges: a small, dense, very hot core fusing helium and a shell around it fusing hydrogen. All this generates a tremendous amount of energy in the star's interior. The result is that the outer layers of the star are pushed outward, far outward. The star balloons in size. As the surface expands, it cools. The once yellow-white star becomes a cooler red star. It has now become a red giant. The term is literal. It is redder in color and gigantic in size compared to before. A star in this phase can swell to tens or even hundreds of times its original diameter. One day, about 5 or 6 billion years from now, our Sun will undergo this transformation into a red giant phase. As it approaches old age, it will exhaust the hydrogen in its core and begin fusing helium. The Sun's core will contract and heat up, and its outer layers will expand dramatically. In the process, the Sun's radius will likely grow so large that it engulfs Mercury and Venus, the two innermost planets, and comes perilously close to Earth's orbit. From Earth's perspective, the Sun would swell to an enormous red orb dominating the sky. The temperature on our planet would skyrocket. In fact, long before the Sun's surface actually reaches Earth, the intense heat will boil away Earth's oceans and atmosphere and render our planet uninhabitable. Essentially, a scorched, lifeless rock. There is a chance Earth might be swallowed up entirely by the Sun's expanded atmosphere, or it might just survive, parched and baked. Either way, the inner solar system will be unrecognizable. The Sun will not only grow in size, it will also lose a lot of its mass via a powerful stellar wind. With less mass, the Sun's gravitational pull on the remaining planets will weaken, causing those planets to drift outward to wider orbits. This red giant phase is a dramatic change, but fortunately for us, it's billions of years away in the future. For a star of the Sun's mass, this red giant stage is essentially the beginning of the end. After perhaps a billion years in the red giant phase, the Sun's core will have fused its helium into carbon and oxygen. It won't be hot enough to fuse those heavier elements, so the core will remain as a hot ball of carbon and oxygen. Without new fusion to support it, the core will contract further, and the outer layers of the Sun, which expanded so far out, will become increasingly unstable. In a series of pulses, those outer layers will be expelled into space, creating a brilliant cloud of gas around the dying star. This glowing shell of ejected gas is called a planetary nebula. The Sun, in its death throes, will thus cast off its atmosphere, which will drift away as an expanding bubble of gas. Planetary nebulae can be stunningly beautiful. Observed through telescopes, they appear as multicolored rings or shapes of glowing gas. In a few tens of thousands of years, the Sun's shed gases will mix into the interstellar medium, enriching it with elements the Sun made. All that remains of the Sun at this point will be its former core. This exposed core is a hot, extremely dense orb about the size of Earth. It's called a white dwarf, the final state of a low to mid-mass star like our Sun. A white dwarf no longer has fusion happening in its center. It is supported against further collapse by quantum pressure. It is, essentially, a stellar ember, an extremely hot cinder left over from the star's life. When it first forms, a white dwarf is incredibly hot and glowing white, blue, but it's also very small, so its total light is relatively faint. Over billions of years, it will cool and fade. To appreciate just how dense a white dwarf is, it packs roughly the mass of the Sun into a volume the size of Earth. Imagine compressing something as massive as a star into a ball only 8,000 miles across. The density of such an object is mind-boggling, on average about 1 million times denser than water, meaning a single cubic centimeter of white dwarf material would weigh on the order of 1 ton. In other words, a teaspoon of white dwarf matter would weigh several tons here on Earth. The gravity on its surface would be hundreds of thousands of times stronger than Earth's. If you somehow stood on a white dwarf, you would feel yourself weighing so much that you'd be crushed instantly. Over a very, very long time, a white dwarf will radiate away its heat and cool down. Eventually, after many tens or hundreds of billions of years, it would become a black dwarf, essentially a cold, dark, stellar remnant. In the case of our Sun, this is its ultimate fate, to spend eternity as a faint white, hot star gradually cooling into darkness. Indeed, most stars end their lives quietly as white dwarfs, simply cooling and fading away. Only the most massive stars end in the spectacular supernova route. Now consider a star much more massive than the Sun, say a star born with 10 or 20 times the Sun's mass, or even more. These stars go through their lives much more quickly and violently. They too will leave the main sequence once their core hydrogen is exhausted, but the sequence of events is even more extreme. Such a star becomes a red supergiant instead of a mere giant. One of the best known examples of a red supergiant is Betelgeuse, the bright reddish star in Orion's shoulder. Betelgeuse is about 15,020 times as massive as the Sun and has expanded to a tremendous size. Observations estimate it is on the order of 700–800 times the Sun's radius. If Betelgeuse were placed at the center of our solar system, it would extend well past the orbit of Mars and possibly even approach Jupiter's orbit. It's so large that its volume would encompass tens of millions of suns. And Betelgeuse isn't even the largest star known. A few rare hypergiant stars, such as UY Scuti or Stephenson 218, are believed to have radii around 1,500 × 2,000 times that of the Sun. Truly monstrous stars. These colossal stars are extremely luminous and short-lived. Betelgeuse, for instance, is only on the order of 10 million years old, yet it is already in its dying phase. In fact, Betelgeuse is expected to explode as a supernova in the relatively near future. It could happen anytime in the next 100,000 years, which is a blink of an eye for a star. It might be tomorrow, or it might be far beyond our lifetimes. We can't pinpoint exactly when, but we know the star is nearing the end of its life. When Betelgeuse does explode, it will likely shine as bright as the full moon in our sky for a few weeks and be easily visible even in daytime. What leads a star like Betelgeuse, or any other massive star, to such a violent end? The difference lies in what happens in the star's core after the hydrogen is used up. A high-mass star has the gravity and pressure to push the boundaries of fusion much further than a star like the Sun can. When hydrogen in the core runs out and the core contracts, the temperature soars high enough to ignite the fusion of helium into carbon and oxygen. Once helium in the core is exhausted, the core contracts and heats again, and the star's envelope expands into a red supergiant. But in these behemoths, the core gets hot enough to start fusing carbon into heavier elements. The pattern continues in a kind of fusion cascade. Carbon fuses into neon, magnesium, and sodium. When carbon is depleted, the core contracts and heats, and then neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron and nickel. The star builds up onion like layers of fusion shells. Hydrogen burning in an outer shell, helium burning in a shell beneath that, carbon burning in a shell closer in, and so forth, all the way to a growing iron core in the center. The iron core is the final product of fusion, because fusion of iron doesn't release energy, it consumes energy. That's a crucial point. Up until iron, fusion can power the star, but once the core accumulates iron, further fusion would not yield net energy. So, as iron builds up in the core of a massive star, the star is living on borrowed time. The star continues burning elements in shells around the core, piling more and more iron into the center. Meanwhile, the time spent on each successive fuel is shorter and shorter. A massive star might spend millions of years fusing hydrogen, maybe 1 million years fusing helium, but perhaps only a few years fusing carbon, a few months fusing oxygen, and mere days fusing silicon into iron. Eventually, the iron core reaches a critical mass. At that moment, the star can no longer support its own weight. For a massive star, this is the final act, and it's dramatic. When the iron core can no longer hold itself up, it collapses catastrophically under gravity. This collapse happens incredibly fast. In under a second, the core implodes. The temperatures in the core skyrocket, and atomic nuclei get crushed together. Protons and electrons merge into neutrons, so the core essentially becomes one giant atomic nucleus, a ball of neutrons. The collapse is suddenly halted by the degeneracy pressure of neutrons. In that instant, the infalling material rebounds off the stiff neutron core. a powerful shockwave is sent roaring outward through the star's interior. The core collapse and rebound is so intense that it unleashes an enormous burst of neutrinos and a tsunami of energy. The star's outer layers are blown off in one of the most violent events in the universe, a supernova explosion. If the core of the star at the time of collapse is below about 2003 solar masses, it will become a neutron star, the ultra-dense, city-sized stellar remnant composed almost entirely of neutrons. If the core is above that mass threshold, even the neutrons cannot halt the collapse, and the core will continue collapsing into a black hole, a point of practically infinite density. Either way, the core's collapse triggers the supernova blast. In a supernova, the star's entire outer structure is ripped apart. The star's brightness increases tremendously for a short time. A supernova can briefly outshine an entire galaxy of normal stars. Imagine a single star suddenly shining brighter than 100 billion stars combined. That is what a supernova can do. It will radiate as much energy in a few weeks as the sun will in its entire 10 billion year lifetime. If such an event happens relatively nearby, it can be visible from Earth, even in the daytime. Human astronomers have indeed witnessed supernovas in the past. Historical records from East Asia and the Middle East describe guest stars appearing in the sky. For example, in 1054 AD, Chinese astronomers noted a new star that was visible in daylight for weeks. This was a supernova. Another supernova was observed in 1604. More recently, in 1987, a star exploded in the Large Magellanic Cloud and could be seen by the naked eye. In our own Milky Way, no supernova has been observed in the past 4 centuries, but statistically, we expect a few per century meaning we could be due for another any time in the future. In the chaotic violence of a supernova, there is a remarkable silver lining. This is the event that forges many of the heavy elements that enrich the universe. During the star's normal life, it created elements like carbon, oxygen, and silicon in its core. But elements heavier than iron, such as gold, platinum, and uranium, require the extreme conditions of a supernova to form. In the supernova blast, atomic nuclei slam together in rapid fire reactions, building up many of the heaviest elements on the periodic table. The explosion then scatters these newly forged elements out into space. The stellar ashes, carbon, oxygen, calcium, iron, gold, and so on, are flung far and wide, mixing into the gas between stars. Supernovae are therefore cosmic gardeners, seeding the interstellar medium with the ingredients for future generations of stars and planets. The very material that makes up our Earth and our bodies has gone through this cycle. The iron in your blood, the calcium in your bones, the oxygen that you breathe, those atoms were once created in the interior of a star or in a supernova explosion. As a NASA astrophysics team put it, we truly are made of stardust. The calcium in your teeth, the iron in your hemoglobin, the carbon in your DNA, all were forged in stellar furnaces. Indeed, without the carbon, oxygen, nitrogen, and other elements spread by stars, Earth could not have solid ground, air, or water, and life as we know it would be impossible. We owe our existence to stars that died long before the Earth formed. Indeed, without the heavy elements from stars, there would be no rocky planets, no air or oceans, and no living beings. Meanwhile, what's left of the star's core becomes either a neutron star or a black hole, as mentioned. Neutron stars are fantastical objects. Imagine something more massive than our sun crushed into a sphere only about 20 kilometers across. They are so dense that a single teaspoon of neutron star material would weigh around 1 billion tons on Earth. The gravity on its surface is so strong that if you dropped an object from 1 meter above, it would hit the surface in a microsecond, accelerating to millions of kilometers per hour. Neutron stars often spin rapidly, Some rotate multiple times per second and emit beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep around like lighthouse beams. If such a beam points toward Earth periodically, we see pulses of radiation. These are observed as pulsars. The first pulsar was discovered in 1967 as a mysterious radio pulse every 1.3 seconds, so regular that the discoverers jokingly nicknamed it LGM-1, half, seriously wondering if it was a signal from an alien civilization. We now know it was a rapidly spinning neutron star. Pulsars can spin unbelievably fast. The fastest known pulsar rotates more than 700 times per second. Imagine an object more massive than the Sun, spinning hundreds of times a second. It defies the imagination. Some neutron stars, called magnetars, have magnetic fields even more extreme, up to 1,000 times stronger than a typical pulsar. A magnetar's field is so extraordinarily powerful that, at a few thousand kilometers away, it could disrupt electronics on Earth. Occasionally, magnetars undergo starquakes that release giant flares of X-rays and gamma rays. If the star's remnant core was too massive to form a stable neutron star, it continues collapsing beyond even the neutron stage. In that case, the core becomes a black hole, an object with gravity so intense that nothing, not even light, can escape from its vicinity. A black hole formed from a single star might contain, say, 5 or 10 solar masses of material, but all of that mass is crushed down into an infinitesimally small volume at the center. The region around it from which not even light can escape is called the event horizon, effectively the point of no return. For a black hole with the mass of our Sun, the event horizon would be only about 3 kilometers in radius. If the Sun was somehow compressed into a sphere only 6 kilometers across, it would become a black hole. For something as massive as Earth, the event horizon would be barely a centimeter across, meaning Earth would have to be crushed to the size of a marble to turn into a black hole. These numbers illustrate how incredibly dense and compact black holes are, matter and gravity in their most extreme state. Because no light comes from a black hole itself, we cannot see a black hole directly as a glowing object. A lone black hole floating in space would appear truly black, a gravitational trapdoor in the cosmos. However, we can detect black holes by their effects on surrounding matter. Often, a black hole will have gas around it. That gas forms a swirling accretion disk as it spirals into the black hole, and it gets extremely hot, often emitting X-rays that telescopes can detect. We also observe stars orbiting an invisible mass. For example, the center of our Milky Way galaxy has stars whipping around an unseen object, which we know is a supermassive black hole. In recent years, astronomers have even managed to capture direct evidence of black holes by imaging their silhouettes. In 2019, the Event Horizon Telescope project released the first picture of a black hole, or rather, of the glowing gas around a black hole's event horizon. It showed a ring of light and a dark central shadow, exactly as predicted by physics. This was the supermassive black hole in a distant galaxy. And in 2022, we finally saw a similar image of the supermassive black hole at our own galaxy's center. Black holes, once purely theoretical, are now actively studied cosmic phenomena. Amazingly, even after a star has died, its story might not be completely over. Sometimes, the remnants left behind can have dramatic afterlives. For example, if two neutron stars eventually orbit each other, they will gradually spiral inward over time. After millions of years, they may collide in a spectacular event called a kilonova, a merger explosion even more energetic than a typical supernova. Such mergers produce strong bursts of gravitational waves that propagate outward. In 2017, scientists detected gravitational waves from a neutron star collision and also saw a flash of light from it. This was the first time we observed both gravitational waves and electromagnetic radiation from the same event. That neutron-star merger forged copious amounts of heavy elements and scattered them into space. Black holes can merge with each other too. When they do, they emit a flood of gravitational waves. We can't see the merger, but detectors on Earth can hear the fabric of space tremble. In 2015, LIGO observed such signals for the first time, confirming a major prediction of Einstein's theories. These phenomena show that even in death, stars can continue to influence their surroundings in extraordinary ways. After a supernova fades, all that remains of the star may be a dense remnant, plus an expanding cloud of gas and dust, the supernova remnant. The ejected material from the star, now racing outward, sweeps up the surrounding interstellar gas and dust, creating a shell or complex filamentary structure that can glow for tens of thousands of years. The Crab Nebula, for instance, is the beautiful filamented remnant of the supernova of 1054 AD, still expanding at thousands of kilometers per second. Over time, these remnants disperse and mix with the interstellar medium, and here the grand cycle turns anew. The scatterings of old stars eventually become part of new nebulae, providing the enriched raw material for future stars. The next generation of stars will form out of clouds, seeded with the heavy elements of previous generations. Our Sun is thought to be a late generation star, born roughly 4.6 billion years ago from a nebula already seeded with heavy elements by earlier supernovae. Those elements made it into our Earth and into us. We truly are, as the saying goes, children of the stars. Stars, then, are not only beacons of light, but cosmic alchemists and recyclers. Through their life cycles, they transform the primordial hydrogen and helium into a rich array of heavier elements. And through their deaths, they redistribute those elements across space to fertilize new star formation. Generations of stars have built up the carbon in our tissues, the oxygen in the air, the silicon in rocks, and every atom of every element heavier than helium. The universe began with mostly hydrogen and helium, and it is the stars that fashioned all the rest inside their hot cores. It's a magnificent ongoing circle of stellar evolution and renewal, star birth, star life, star death, and new stars born from the remnants. This cycle has been going on for billions of years and will continue for billions more. It is the engine that drives the chemical enrichment and dynamic evolution of galaxies. When we survey the night sky filled with stars, we are gazing at a vast cosmic ecosystem in action. Each pinpoint of light has its own history and future. Some of those stars may be like our Sun, gently burning for eons. Others might be giant stars soon to explode, or faint red dwarfs just chugging along. There are hundreds of billions of stars in the Milky Way galaxy alone, and beyond that, billions of other galaxies each with their own billions of stars. The total number of stars in the observable universe is estimated to be around 10 to the 22. That's a 1 with 22 zeros after it. This number is so huge that it defies true comprehension. One popular comparison is that there are more stars in the universe than grains of sand on all the beaches on Earth. In fact, astronomers estimate there are on the order of 10,000 stars for every grain of sand on Earth. It's an astonishing thought. Next time you're at the beach, pick up a handful of sand and consider that the stars outnumber those tiny grains. Every one of those stars is a sun, and many of those suns have their own families of planets. The universe is teeming with stars beyond counting. Understanding the life cycle of stars gives us a profoundly richer appreciation of the night sky. When you next gaze up at the stars, remember that those twinkling lights are not mere points. They are distant suns, each with a life story spanning eons. The star that looks like a pinprick could be a giant blazing at millions of degrees, or a diminutive red ember glowing softly. Some of the stars you see tonight might already have exploded in the far past, their light only now arriving at Earth after traveling for centuries through space. In a very literal sense, we are connected to these stars. Our planet and our bodies are composed of star-born atoms. Indeed, without the heavy elements forged in stars, Earth wouldn't exist as a rocky world, and human beings could not have come to be. As the late astronomer Carl Sagan famously said, "We are made of star stuff." We are the universe's way of knowing itself, formed from the ashes of long dead stars.
In the end, the saga of stars is the saga of the universe. It's a story of creation and transformation on an epic scale, of diffuse gas gathering to ignite nuclear fire, of shining stability and convulsive death, of elements forged in celestial furnaces and cast into the darkness to become the seeds of new worlds. Stars have illuminated the cosmos for over 13 billion years, and they will continue to do so long into the future. Every twinkling star in the sky is a testament to the ongoing cycle of cosmic birth and rebirth. So the next time you find yourself under a starry night, take a moment to ponder the incredible processes happening above you. Those stars are distant suns, forging the stuff of life, exploding and renewing the galaxy. They light up the darkness and spark our imaginations. Theirs is a never-ending story, one of fire and dust, life and death, and renewal. An endless cosmic dance that has shaped our universe and, ultimately, made our own existence possible. And as long as you can see the stars shining overhead, you are witnessing a part of that grand story unfolding, a story that connects us all to the cosmos and to the dazzling stars that fill the sky. The final glow of the previous story fades, but our journey among the stars is far from over. In fact, it's only just beginning. Out in the cosmic dark, countless stars still beckon with new mysteries and deeper roles to explore. We have gazed upon the life cycles of stars, their births in nebulous cradles and their deaths in explosive finales. Yet there is even more to the stellar saga. Now, let us venture further into the galactic tapestry to uncover how stars themselves shape the grand story of the universe. As we continue, imagine drifting back in time to an era before even the first star ignited. In that primordial darkness, over 13 billion years ago, the universe waited for its first light. When the first generation of stars were finally born, they were unlike any that exist today. These population 3 stars, as astronomers call them, were forged from only the simplest elements, the sole ingredients created by the Big Bang. Theory paints them as cosmic titans, perhaps 30 to 300 times the mass of our Sun, and millions of times brighter. Such massive stars would burn their fuel ferociously fast, blazing only a few million years before dying in titanic supernova explosions. Yet in their brief lives, they performed a vital service. Their searing ultraviolet light rayonized the universe's hydrogen, ending the cosmic dark ages nearly 1 billion years after the Big Bang. In those first brilliant sparks, the universe transitioned from dark and opaque to radiant and transparent, a fundamental turning point in cosmic history. When those primordial stars lived and died, they also created something entirely new: heavy elements. In their hot cores, nuclear fusion began forging elements heavier than helium, carbon, oxygen, silicon, and more. And when the first stars perished as supernovae, they seeded the cosmos with these heavier elements. Before stars, the universe lacked the ingredients for planets or life. After the first stars, space was enriched with the star stuff from which future generations could build. It's awe-inspiring to realize that nearly all the elements in our bodies, the calcium in our bones, the iron in our blood, the oxygen we breathe, were forged in the hearts of stars that lived long ago. Those early explosions scattered the raw materials for new stars, new planets, and eventually us. Little wonder that astronomer Carl Sagan's poetic truth resonates. We are made of star stuff. The universe had to go through the fires of stellar furnaces,
to fill the periodic table beyond hydrogen and helium. With each generation of stars enriching the cosmic brew, subsequent stars were born with higher metallicity. Thus began an ongoing chemical evolution, each stellar generation shaping the composition of the next, gradually building up the complexity needed for rocky worlds and living beings. In the wake of the first stars, new generations of stars began to form from the ashes. Astronomers classify these stellar populations by their metal content. The ancient stars that followed the primordial ones are dubbed Population 2. They contain only a small trace of heavy elements, just a smattering inherited from those first supernovae. Many Population 2 stars still shine today. They are the oldest stars in galaxies, often found in the halos of galaxies or in ancient globular clusters. In fact, some globular star clusters in our Milky Way are nearly 13 billion years old, almost as old as the universe itself, and their stars preserve a fossil record of the early cosmos. These venerable suns are cosmic time capsules, their faint metal content telling us they formed when the universe was still poor in heavy elements. By contrast, Population Y stars, like our own Sun, are rich in heavier elements. Population I stars are younger, born later in cosmic history, from gas already recycled and enriched by countless prior stellar lives. They reside mostly in galactic disks and include many bright, hot stars, as well as middle-aged stars like the Sun. The distinction between these populations isn't just academic. It's central to understanding how galaxies formed and evolved. In the Milky Way, for example, the spherical halo of old Population 2 stars may be remnants of the galaxy's original build and early mergers, whereas the disk's Population 1 stars reflect ongoing star formation fueled by interstellar gas. The very structure of our galaxy, a thin disk with spiral arms, a central bulge, and a diffuse halo, has been shaped by the continuous birth and death of stars over billions of years. Early in our galaxy's youth, it likely underwent titanic mergers with smaller protogalaxies. One dramatic merger, revealed by the European Gaia spacecraft's star mapping data, occurred around 10 billion years ago when the Milky Way swallowed a dwarf galaxy, now nicknamed Gaia Enceladus, or the Gaia Sausage. This cosmic collision delivered a vast influx of stars into the Milky Way's halo. The evidence is written in the motions and chemical makeup of many halo stars, which are distinct from native Milky Way stars, a sign that they originated in another galaxy. During such mergers, bursts of star formation likely ignited as gas clouds were jolted and compressed. Thus, the Milky Way's early history, the thickening of its disk, the build up of its stellar halo, was driven in part by starbirth sparked in the chaos of mergers. Time and again, galaxies grew by merging and forming new stars, with each generation of stars influencing the galaxy's structure and dynamics. Star formation itself tends to be a self-limiting and self-propagating process. Massive young stars radiate intense light and spew stellar winds, which can carve cavities in the surrounding gas. When the most massive of these stars go supernova, they blast the gas with shockwaves. This feedback can either trigger new stars or quench star formation. In dwarf galaxies, a few vigorous supernovae can blow out much of the gas, stifling further starbirth. In larger galaxies, star formation and supernova feedback regulate each other in a complex dance, ensuring that galaxies don't convert all their gas into stars at once. Indeed, observations show that the universe's star formation rate peaked about 10 to 11 billion years ago and has been declining ever since. At its height, galaxies were forming stars at a frenetic pace, so much so that today's rate is only a few % of that peak. Over billions of years, much of the free gas in galaxies has been used up or locked into stars, and energetic feedback from stars has kept a lot of remaining gas too hot to collapse easily. Our cosmos is slowly simmering down. Still, new stars continue to be born even now, especially in the rich spiral arms of galaxies. In our Milky Way,
Stellar nurseries like the Orion Nebula are actively turning out fresh stars. But the overall trend is inexorable. The fuel for star formation is finite, and eventually it will run low. Gazing far into the future, astronomers estimate that in roughly 100 trillion years, all the usable star-forming gas will be exhausted or locked up. By that far epoch, the era of star formation will draw to a close. The universe will transition into a quieter stage, dominated by the embers of stellar evolution. Myriad white dwarfs slowly cooling into black dwarfs, neutron stars and black holes lurking in the darkness, and only the occasional new star flickering to life from the rare merger of two old stellar remnants. But fear not. At present, the universe is still richly populated with shining stars, and we live in a cosmos that is very much alive with stellar light. Let's turn our attention to the stars as architects of their galaxies. Every galaxy's visible beauty, its shimmering starlight, its glowing nebulae, comes from stars. Stars delineate the spiral arms of disk galaxies, with luminous young star clusters tracing out spiral patterns like celestial fairground lights. In majestic barred spirals and elegant ellipticals alike, the collective light of billions of stars gives each galaxy its form and color. Hot, young stars glow blue, white, giving star-forming galaxies a bluish hue, while older, cooler populations lend a yellow-red warmth to galaxy bulges and ellipticals. Thus, the mix of stellar ages influences a galaxy's appearance. A young, actively star-forming galaxy looks very different from an old, evolved system, precisely because of its stars. Over cosmic time, galaxies can even change type as their star formation slows. A disk galaxy may fade and redden into something more akin to an elliptical if star birth ceases and its blue stars die out. The grand narrative of galaxy evolution is intimately tied to the cycles of star formation within. Now consider not just individual stars, but stars in pairs and groups. It may surprise you to learn that most stars in the sky are not solitary like our Sun, but part of binary or multiple star systems. Imagine two stars locked in a gravitational waltz, orbiting a common center of mass. Such binary star systems are incredibly common, by some estimates, more than half of all Sun-like stars have a stellar companion. In these systems, stars can profoundly affect each other's evolution. Sometimes one star will swell into a red giant and transfer mass to its companion, an event that can spark explosive outbursts or novae. In fact, one type of supernova occurs in an elderly binary. A dense white dwarf star siphons gas from a companion until a runaway explosion is triggered, obliterating the white dwarf. These Type Ia supernovae are immensely important standard candles that have helped astronomers measure cosmic distances and the expansion of the universe. The discovery of the accelerating expansion of the universe, and hence dark energy, hinged on observations of distant Type Ia supernovae. Thus, an intimately interacting binary pair on the stellar scale produces a beacon visible across billions of light years, allowing us to gauge the universe's fate. In other binaries, two massive stars might evolve in tandem and eventually merge or collide. In globular clusters, such stellar collisions can produce the enigmatic blue straggler stars, stars that appear unexpectedly young and blue in a cluster of otherwise old stars. Blue stragglers are thought to form when two stars coalesce into a single, more massive star, effectively rejuvenating it. The result is a star that stands out as bluer and more luminous than it should for the cluster's age, a literal stellar oddball that reveals the cluster's dynamic past. The overcrowded cores of globular clusters facilitate such collisions, offering yet another example of how stellar interactions can yield peculiar outcomes. Some binaries consist of extremely exotic partners, for example, a neutron star or black hole orbiting a normal star. These systems can produce astonishing phenomena,
like X-ray binaries and even the recently detected gravitational waves. Picture a dense neutron star, essentially a city-sized atomic nucleus with the mass of the Sun, pulling gas off a companion star. As the gas spirals in, it heats up and emits powerful X-rays, making the binary shine brightly in X-ray light. In 1967, astronomers discovered pulsars. The first was affectionately nicknamed LGM-1 for Little Green Men 1, because its precise radio pulses were so mysterious, they were jokingly suspected to be alien signals. Soon, pulsars were understood as rotating neutron stars, the collapsed remnants of supernova explosions. In some binaries, two neutron stars orbit each other, gradually enspiraling as they radiate gravitational waves. In 2017, humanity observed for the first time the space-time ripples from such a neutron star merger, along with a dazzling multi-wavelength light show called a kilonova. That single event confirmed that neutron star collisions forge many of the universe's heaviest elements and demonstrated how closely stellar death and cosmic alchemy are intertwined. Similarly, the first direct detection of gravitational waves in 2015 came from a merger of two stellar mass black holes, remnants of massive stars that had danced together until coalescing. These gravitational wave discoveries opened a whole new window on the universe, essentially hearing the sound of stars merging in the dark. Through binaries and their sometimes violent interactions, stars have enabled us to confirm Einstein's theories, understand extreme states of matter, and even create new fields of astronomy. While many stars live in pairs or clusters, our Sun stands alone. Yet the Sun is no less influential for its solitude. It anchors our solar system, and its steady light allowed life to flourish on at least one world. The Sun's story is still unfolding. About 5 billion years from now, it will swell into a red giant, becoming so large that it engulfs Mercury and Venus, and possibly Earth as well. By then, Earth will be a scorched cinder. As the Sun expands, it will also begin to blow off its outer layers. In its death throes, it may create a beautiful planetary nebula, a glowing shell of expelled gas, before finally settling down as a white dwarf. This stellar remnant, about the size of Earth but containing nearly half the Sun's mass, will slowly cool like a fading ember for trillions of years. That is the long-range fate of our Sun and stars like it, to quietly shed their outer envelopes and leave behind dense cores. The galaxy will become littered with these white dwarfs, cosmic embers that, though faint, carry the memory of their progenitor stars. Even in death, stars continue to shape their surroundings. When a massive star explodes as a supernova, it leaves behind either a neutron star or a black hole. The expanding supernova remnant, a glowing cloud of ejected material E, can crash into surrounding clouds and trigger new rounds of star formation. Think of the Crab Nebula, the remnant of a supernova observed in 1054 AD. At its center lies a whirling pulsar energizing the nebula, and around it, the expanding filaments are rich in elements like oxygen, nitrogen, and iron, synthesized in the star's final moments. Those elements will eventually mix into interstellar space, seeding future molecular clouds. In this way, each supernova is both an ending and a beginning. An ending for a massive star, but a beginning for new stars that will one day condense from the enriched debris. Meanwhile, the neutron star left behind pours out winds of high-energy particles, sculpting and illuminating the nebula. A stellar corpse can thus continue to inject energy into the galaxy's ecosystem long after the star's death. Black holes, too, play a role. If a stellar mass black hole devours gas or stars, it converts that mass to energy, impacting the ambient gas. And on a galactic scale, supermassive black holes lurking in galaxy centers, themselves the end, products of stellar processes and mergers, can profoundly influence star formation in their host galaxies by blasting out energy. But those supermassive black holes are a tale for another time. In our story, we focus on the stars themselves, the little black holes they leave behind, and how even those contribute to the cosmic tapestry. Consider for a moment the sheer number of stars out there. Our Milky Way alone holds on the order of 100 to 400 billion stars. It's a figure almost beyond comprehension. And yet, the Milky Way is just one of perhaps hundreds of billions of galaxies in the observable universe. If each of those has 100 billion or so stars, you get numbers like 10 more 22 stars in the observable universe. That's a 1 with 22 zeros after it, a quantity of stars truly staggering to contemplate. Each of those stars is a potential sun, perhaps with its own family of planets. In recent decades, we've learned that planets abound around other stars. The once singular idea of another solar system has given way to the realization that planetary systems are commonplace. Using missions like Kepler and TESS, astronomers have detected over 5,000 confirmed exoplanets so far, and counting. Statistics indicate that perhaps 1 in every 5 sun-like stars harbors an Earth-sized planet in its habitable zone. This means when you gaze up at the night sky, statistically the nearest sun-like star with an Earth-ish planet might be only a dozen light years away, practically next door on the cosmic scale. Planetary systems come in a dizzying variety: hot Jupiters skimming their stars' surfaces, multi-planet systems packed in tight orbits, planets around double stars, and even planets orbiting the crushed remnants of dead stars. There are even planets wandering alone in the dark of interstellar space. Stars and planets are inseparable companions in the cosmic story, and just as stars give birth to planets, planets can influence stars in subtle ways.
Take our solar system. The sun's activity and stability have been key to life's development on Earth. Our sun is a rather steady star, but not all stars are so calm. Many young stars and red dwarfs are highly variable and prone to flares. Variable stars in general constitute a broad category, including stars that intrinsically pulsate, erupt, or have eclipsing companions, causing dips in light. These variations have made certain stars vital tools for measuring cosmic distances. For instance, the Cepheid variables, luminous pulsating supergiants, have a well-defined relationship between their pulsation period and true brightness. Discovered by Henrietta Leavitt over a century ago, this relationship allows astronomers to determine a Cepheid's distance by comparing its known true brightness to its observed brightness. Using Cepheids as standard candles, Edwin Hubble measured the distance to the Andromeda galaxy in the 1920s, discovering that Andromeda lay far outside our Milky Way, thus proving that the universe is populated with myriad galaxies. Later, Cepheids and Type Ia supernovae would help establish that the universe is expanding and, in fact, accelerating in its expansion due to mysterious dark energy. It's poetic that the rhythmic beating of variable stars' light has served as a cosmic yardstick, allowing us to map the universe at large. A throbbing Cepheid in a distant galaxy becomes a beacon, indicating that galaxies' distance, and hence offering insight into the scale of the cosmos. Not all variable stars are so regular and helpful. Some are downright capricious. There are flare stars that can double in brightness in minutes, eruptive variables like young stellar objects that burp out bursts of light as they gulp down fresh gas from their surroundings, and giants like Mira, a star in Cetus that pulsates over many months, varying so much that it can nearly disappear from view and then return. And who could forget the recent drama of Betelgeuse, the red supergiant shoulder of Orion? In late 2019, Betelgeuse dimmed startlingly, losing 2/3 of its brightness, causing speculation that it might be about to explode as a supernova. Observations eventually indicated that Betelgeuse had likely ejected a cloud of dust that temporarily obscured its light from our vantage point.
By mid-2020, Betelgeuse returned to normal. This episode was a vivid reminder that stars are dynamic, evolving entities, not static points of light. Betelgeuse is expected to go supernova sometime in the next 100,000 years, a blink of an eye in cosmic terms, and when it does, it will light up our sky brilliantly for weeks, a spectacular final act for a star perhaps 15,020 times the Sun's mass. If we're lucky enough to witness it, that supernova will be a momentous event in human skywatching history. But even short of such cataclysms, the variability of stars teaches us about their inner workings. Through the field of astroseismology, astronomers study tiny pulsations in stars to infer their internal structures, analogous to how geologists use earthquakes to probe Earth's interior. Our Sun, too, has a mild 11th-year cycle of activity, modulating its sunspots and flares, which subtly affects solar output. Thankfully, the Sun's variability is slight. A more erratic star might have made Earth's climate far less stable for life. Stars, then, are creators, testers, and timekeepers of the universe. They create the elements that form planets and people. They test the laws of physics in extreme conditions, from nuclear fusion in cores to relativistic speeds in neutron stars. They serve as timekeepers by revealing cosmic distances and ages through their life stages and variable rhythms. And collectively, stars brighten the universe, turning the primordial darkness into a cosmos of light and color. It is sobering and fascinating to realize that the universe's era of starlight is, in a sense, a finite chapter. We live roughly in the middle of this chapter. For billions of years before stars, the universe was dark, and trillions upon trillions of years in the future, after the last stars have flickered out, the universe will go dark again. But right now, and for many eons to come, it is the age of stars. An age in which galaxies sparkle and life has the opportunity to arise on warm, sunlit worlds. The story of stars is also the story of continuity and renewal. Massive stars live fast and die young, but in doing so, they trigger new growth around them. We see this in regions like the Carina Nebula, where the death of one generation seeds nebulae that birth the next. In a spiral galaxy's life, waves of star formation move through the disk, often stimulated by spiral density waves or past encounters with other galaxies. Our own Sun likely formed in a cluster with dozens or hundreds of other stars about 4.6 billion years ago, possibly triggered by a nearby supernova explosion that compressed our natal cloud. Traces of that supernova may be preserved in certain isotopes found in meteorites from the early solar system. Thus, the Sun and planets might owe their existence to the death of a long-gone massive star. Indeed, each of us carries the ashes of ancient supernova inside our bodies. The iron in your blood was forged in a star that exploded billions of years before the Sun even existed. In a very literal sense, stars are our cosmic ancestors. As we look ahead, what new revelations about stars await us? We stand in an exciting era of astronomy. The James Webb Space Telescope is now peering into the deep cosmos, possibly capturing light from some of the first galaxies and stars that formed over 13 billion years ago. Already, Webb has identified candidate galaxies so far away that they challenge our understanding of how quickly stars and galaxies could have formed. In the coming years, Webb may indirectly detect evidence of population 3 stars, or at least constrain their properties by observing the distant galaxies they inhabit. On the other end of the spectrum, Webb and other observatories are turning their gaze to exoplanet atmospheres, reading the fingerprints of molecules like water vapor, carbon dioxide, and methane as starlight filters through alien skies. In 2022, JWST made the first clear detection of carbon dioxide in an exoplanet's atmosphere, a proof of concept for the detailed atmospheric analysis of potentially habitable worlds in the future. We are learning to read the chemical weather reports on planets dozens of light years away, an astounding development. Future missions will go even further. The upcoming Nancy Grace Roman Space Telescope will conduct vast surveys of the Milky Way's center, potentially discovering thousands of new exoplanets through microlensing and mapping out the distribution of stars and dark matter with high precision. The European Extremely Large Telescope, a 39-meter behemoth currently under construction, will in the next decade directly image some exoplanets and dissect the light of stars in distant galaxies, perhaps even detecting biosignature gases on rocky planets around nearby stars. It is mind-boggling. We are on the cusp of potentially finding evidence of life beyond Earth by examining starlight passing through a distant planet's atmosphere. Should we succeed, it would be a profound confirmation that we are not alone, all made possible by the interplay of stars and their planets. Even without finding life, the future of stellar astronomy is bright. New observatories will allow us to watch stars in real time in unprecedented ways, catching the precise moment a star goes supernova in our galaxy, or detecting the subtle vibrations of stars across our galaxy to decode their ages and compositions. We might witness phenomena we've only theorized, perhaps the birth of a black hole accompanied by a flash of neutrinos and gravitational waves, or the mergence of two white dwarfs into a new star or a supernova. We may even discover new classes of stars. Who knows? Throughout history, whenever we have opened new eyes on the universe, we've stumbled upon surprises. There could be rare types of stellar objects out there awaiting discovery, stars powered by exotic physics, or stars caught in transitions never before seen. The universe tends to be creative with its use of the physical laws. From the first luminous beacons that banished the cosmic night, to the ordinary middle-aged sun that sustains life on a blue planet, to the spectacular supernovae and gravitational wave chirps that herald stellar deaths. Stars have been the main protagonists in the cosmic drama. They are the alchemists that forged the elements, the lighthouses that guide our explorations, and the engines driving the evolution of galaxies. As we float here on our tiny world, bathing in the gentle sunshine of our star, we remain intimately connected to the lives of stars across the universe. Every atom of calcium in your bones was fused in a star that lived long ago and far away. Every gentle sunset tinged with reds and oranges is a reminder that our sun, too, will one day swell and cast a red hue over the sky of whatever beings inhabit Earth in the distant future. Yet even as individual stars perish, the universe ensures the torch of light is passed on. New stars ignite from the ashes, continuing the cycle. And so, the cosmic roles of stars are as profound as they are varied. Stars are creators of light, of elements, of new beginnings. Stars are destroyers. In their violent ends, they can obliterate companions or outshine entire galaxies for a time. Stars are storytellers. Their compositions and motions recount the history of their galaxies. Stars are guideposts. Their steady pulsations and explosions have built our cosmic distance ladder and expanded our knowledge of the universe's expansion. Stars are nurturers, providing warmth and energy to any orbiting planets, and perhaps nurturing life. It is often said that without stars, the universe would have remained a dull, cold fog of hydrogen and helium. There would be no planets, no complex chemistry, and certainly no people to wonder at it all. Indeed, without the stars, the universe would lack its narrative spark. Our exploration of the stars deepens our connection to the cosmos. When we look up on a clear night and see the Milky Way's band of light, we are seeing the integrated glow of billions of distant suns, many of them older, many younger, each on its unique journey from birth to death. Among them are red giants, white dwarfs, neutron stars, perhaps even black holes quietly lurking. All of them together create the shimmering tapestry of the night sky. As we conclude this chapter of the documentary, let's reflect on the awe that stars inspire. For thousands of years, humans have looked to the stars for constancy, for navigation, for myths and meaning. Only in the last century or so have we truly grasped what they are. Nuclear furnaces, balanced by gravity, simple in their basic principles, yet endlessly diverse in their outcomes. And only in the last few decades have we come to see the universe on the largest scales and realize the full extent of the stars' role in shaping everything. The saga of stars is ongoing. Even now, new stars are being born in dusty nebulae. Old stars are blowing themselves apart. Binary stars emerging. Planets are coalescing around nascent suns. Life might be evolving in some distant solar system under the light of an alien star. And photons that left stars billions of years ago are just now reaching Earth, bringing us news from across the universe. With each advance in technology, we become better listeners and observers of the stars' messages. In the near future, we might map the surfaces of stars' light, years away, or detect the faint whispers of stars collapsing into black holes across the universe. And someday, perhaps, we will travel to other stars, our descendants, voyaging across interstellar space to touch those points of light that have beckoned for ages. For now, we continue to study and marvel. The stars have been our beacons, our ancestors, our catalysts. They will continue to shine for billions of years, but not forever. So it is a privilege to exist in this epoch of glittering skies. As our story winds down, step outside on a dark night and look up. Each star you see is part of a grand cosmic ecosystem. Some of those stars are likely orbited by planets you cannot see, perhaps harboring beings who look back at our sun as just another point of light in their sky. In the end, stars connect us across the gulfs of space and time. They are the universals, appearing in the sky of any planet in any galaxy, adhering to the same physics, telling variations of the same tale. This is the cosmic role of the stars, to light up the universe, to forge atoms from the raw stuff of the Big Bang, to sculpt galaxies, to cradle planets, and to continuously renew the cosmos. They are the glittering thread woven through the fabric of space, time, binding the universe together in light. And as long as stars shine, the universe will not be a lonely, lifeless place, for their light creates the possibility for beauty, complexity, and life. The story of stars is the story of how the universe, once a primordial soup of particles, became self-aware through creatures like us. We are the children of the stars, and through us, the stars know themselves. In the ever-continuing cycle of cosmic evolution, the stars have truly shaped the evolution of the universe, and they will continue to do so far into the future. So, whenever you stargaze, remember, you are watching creation in action, witnessing the ongoing drama that made all of existence possible. The tale of the stars is the tale of us all, a story still unfolding, written across the sky in the light of a billion suns. The night is dark and vast, an ancient canvas of silence spangled with stars. Then, without warning, a new light pierces the sky. A soft glow emerges just above the horizon, growing into a brilliant streak that arches across the darkness. It is a comet, sudden, bright, ancient, beyond measure. The sight catches your breath. There is something primeval in this glowing apparition, as if a piece of the dawn of the cosmos has come visiting. It hangs like a celestial torch, its tail a shimmering train of pale light. In that moment of discovery, under that cosmic beacon, you feel the pull of both wonder and reverence. Time seems to slow as the comet's tail unfurls across the stars, a ghostly plume etched in the night. Standing there, you are not merely an observer, you are a participant in an age-old human story of awe. Thousands of years ago, someone like you looked up at such a sight with trembling heart, wondering what it meant. Was it a herald of doom, a dragon of the skies, or a divine messenger? Myths sprang from moments like this. A dragon's fiery breath, a sorcerer's wand, a weeping ghost of a long-dead star. Even knowing the science, you can feel those old echoes. A comet ignites the imagination. Its beauty is laced with a whisper of terror from our ancestors' memories. But armed with understanding, awe overtakes fear. You stand in quiet excitement, aware that you are witnessing a traveler that may have last passed this way when civilizations were young. What exactly is this cosmic wanderer that paints the sky? To the naked eye, it looks like a star with a wispy tail, but in truth, it is something far more intricate. At the heart of the spectacle is the comet's nucleus, a small, solid core, often just a few kilometers across. You cannot see it from Earth, but hidden in the comet's brilliance is that nucleus, a dark, irregular lump of ice and dust, like a frozen capsule of time. As the comet drew nearer to the sun on its long journey, the warmth began to awaken it. Ice locked away for eons began to sublimate directly into gas, jetting out from the nucleus and dragging dust with it. This activity created a fuzzy, luminous cloud around the nucleus, known as the coma. The coma is what gives the comet that hazy star-like head, a diffuse sphere of gas and dust that can swell to tens of thousands of kilometers across, enveloping the nucleus in a glowing shroud. The sunlight and the solar wind, those incessant streams of charged particles blowing outward from the sun, grab hold of the coma and sculpt it into the comet's magnificent tail. In fact, the comet wears not just one tail but often two, one of dust and one of ionized gas. The dust tail, formed by tiny grains pushed gently by the pressure of sunlight, shines with the reflected light of the sun. It often appears curving and broad, a fan of golden white that traces the comet's recent path. The ion tail, made of gases that have been ionized, electrically charged, by solar ultraviolet light, is caught up and carried straight outward by magnetic fields in the solar wind. This tail is usually narrow and straight, often tinted blue from glowing carbon monoxide ions. It points directly away from the sun, a taut streamer of plasma connecting the comet to our star's influence. Tonight, under your gaze, the dust tail of our comet sweeps upward, slightly arched, while a fainter bluish filament, the ion tail, points off in another direction, straight as an arrow away from the sunset. The whole structure is otherworldly, a cosmic plume that dwarfs any planet, yet it emanates from a core no larger than a mountain. It is as if a snowball the size of a city has lit a long torch in the vacuum of space. You marvel at the contradiction, how something so small can create a vision so huge and splendid. But that is the nature of comets, those dirty snowballs of the solar system. They carry within them the potential, under the sun's touch, to become ephemeral giants, with tails millions of kilometers long that can stretch across the sky. As you watch, the comet slowly glides against the backdrop of stars. It moves noticeably from night to night, a visitor on its way through our cosmic neighborhood. This very movement, so slow and stately, hints at the comet's long journey. It came out of the dark, and it will return to the dark, following a grand elliptical path around the sun. Its appearance is a brief performance in the inner solar system, a visit to the realm of sunlight, before it heads back to cold outer reaches. The thought tugs at something in your heart. You are seeing a traveler that has spent most of its life in darkness, far beyond the worlds we know, and soon it will be gone again. There is an almost melancholy beauty to it, this lonely voyager flaring into glory when near the sun, then vanishing for centuries or millennia. And where did it come from, this ancient wanderer? To truly appreciate the comet, one must trace its origin story out to the fringes of the sun's domain. It likely began its journey in the outermost regions of the solar system. a place where countless such icy bodies dwell. Some comets originate in a vast ring of debris just beyond Neptune known as the Kuiper Belt, the same region that harbors Pluto and other dwarf planets. Out there, in the frigid twilight at the edge of the sun's influence, lie innumerable frozen objects. For eons they orbit quietly, like embers left over from the solar system's formation. Every so often, a gravitational nudge, perhaps a slight tug from a passing planet, or the distant alignment of giants, disturbs one of these ice-laden worlds. It gets diverted from its stable path and sent sunward. What was once a remote, frozen chunk, invisible in the darkness, becomes a comet alive with light as it nears the sun. Other comets hail from even farther away, the mysterious Oort cloud, a spherical halo of icy bodies encasing our solar system at incomprehensible distances. The Oort cloud is thought to be a shell of trillions of cometary nuclei, stretching almost a quarter of the way to the nearest stars. Out there, the sun is merely a distant glimmer, and temperatures are only a few degrees above absolute zero. A comet born in the Oort cloud may spend millions of years circling in deep freeze, never coming near the inner planets. But occasionally, the subtle gravitational tides of the galaxy or the brief intrusion of a passing star jostles the Oort cloud. When that happens, one of these ancient icebergs can be dislodged, beginning a slow fall toward the sun. Such a comet arrives from any direction. Unlike Kuiper Belt comets, which travel near the plane of the solar system, an Oort cloud comet can plunge in from the north, south, or anywhere. Many of the great comets of history, those with extremely long periods, or even one-time visitors, began their journeys here, in the solar system's distant comet cradle. Our comet tonight might be one of these long-lost children of the sun, returning for a brief reunion, or perhaps a younger, shorter period comet from the Kuiper Belt, making more frequent trips. In either case, it carries a priceless cargo, the primitive material of the early solar system. These outer regions, whether the Kuiper Belt or Oort cloud, are cosmic deep freezes. They preserve the composition of the solar nebula, the cloud of gas and dust from which the sun and planets formed, nearly unchanged for billions of years. This comet's nucleus is a time capsule from that epoch of creation. Inside it are ices that condensed in the original protoplanetary disk before even Earth existed. Every molecule of water ice, every grain of dust within the nucleus, has a story to tell about the formation of the planets. If one could hold a piece of that nucleus in hand, with thick, insulated gloves of course, you would be holding something almost unchanged since the birth of the solar system. The comet's ice is a mix of water, yes, but also other exotic ices: carbon dioxide, dry ice, carbon monoxide, methane, ammonia, perhaps even more complex compounds like methanol or formaldehyde. These were the ingredients available in the outer regions of the sun's natal disk. Embedded in the ice are particles of rock and dust, silicates and metals that once floated in the protoplanetary cloud alongside the ices. Many of those dust grains are minuscule time travelers themselves, tiny stardust grains that predate our sun, forged in the envelopes of ancient stars and cast into the galaxy before being caught up in the cloud that formed our solar system. Others are fragments that formed near our infant sun and were then flung outward to mix with cold ices, a testament to the turbulent mixing in our solar nursery. Each comet, then, is a miniature museum of solar system history, containing both the coldest ices and traces of the hottest fires from our system's birth. As the comet's nucleus races through space, its ices vaporizing and dust spewing out, it actively sheds this ancient material. The very dust you see glinting in the tail was once part of that primordial nebula, now catching sunlight once again. In a poetic sense, the comet is sharing its memories as it travels by. Its ice is memory, its dust is story. The ice carries the memory of the solar system's infancy, preserving chemical signatures of the era when planets were just coalescing. The dust carries the story, each mote a tale of high heat or interstellar journey, of collisions and condensations long ago. Together, released in the comet's luminous wake, they weave a narrative of creation for those who know how to read it. Scientists have indeed learned to read some of that narrative. Space missions have sampled comet dust, and within those tiny grains, they discovered complex organic molecules, the stuff of life's prelude. It turns out that comets are laden with carbon-based compounds, chains and rings that form easily in the chemistry of interstellar space and protoplanetary disks. When the Stardust probe brought dust from Comet Wild 2 back to Earth, laboratory analyses revealed glycine, a simple amino acid, and a variety of other organic molecules. Think of that, building blocks of life, found in the tail of a comet. And not just one or two. Comets seem to be rich in organics, with some scientists estimating that perhaps half of the dust by mass is composed of complex organic material. These are not living things, but they are the raw ingredients from which living chemistry can spring. In addition, analysis of comet samples and observations shows they often contain a lot of carbon, hydrogen, oxygen, and nitrogen, the very elements that make up our bodies. Phosphorus has been detected too, another element vital for life, present in DNA and cell membranes on Earth. In essence, comets carry a toolkit of life's essentials kept on ice. This realization has dramatically expanded our appreciation for what comets are, not just icy dirt balls, but potentially couriers of life's ingredients across the cosmos. They travel with stores of water, myriad organic molecules, and even simple amino acids, preserved in the deep cold and delivered to any world, lucky or unlucky, enough to cross their path. But these ingredients remain locked within until the comet nears the sun. Only then does the great thaw begin. Right now, as you watch our comet in the sky, the very process that allows us to see it is also a kind of unveiling. Gas and dust from the nucleus are being released and illuminated, giving scientists a brief chance to study what the comet is made of. Telescopes are trained on its spectrum, decoding the chemical fingerprints. Water vapor, cyanide, carbon dioxide, ammonia, yes, all are there, mixing into the night. A comet like this often carries more than 20 or 30 different detectable gases, a cocktail of volatiles that reads like a chemist's notebook of creation. Some of those gases, like a whiff of hydrogen sulfide or ammonia, hint at the complex reactions that occurred in the comet's frozen interior over time, as cosmic rays and sunlight slowly altered the ices. And what of the nucleus itself, that hidden kernel of ice and dust? If we could see it now, we might be surprised. Rather than a pristine white snowball, comet nuclei are often as dark as coal. After countless orbits, or even during a single close pass, a comet's surface can become encrusted with a layer of dark, carbon-rich material, like a charred crust, left behind after more volatile ices sublimate away. This dust mantle dulls the comet's reflectivity, making the surface absorb most sunlight. Indeed, when spacecraft finally photographed comet nuclei up close, they appeared charcoal black, peppered with bright jets where geysers of sublimating ice burst through the crust. So our comet's brilliant display hides a secret. Its core is likely a somber, dark wanderer, illuminated only by the halo of its own making. Deep within that core, shielded perhaps by layers of dust, there may remain ices that have not been touched by warmth since the beginning. Those inner ices will keep the comet's ancient memory intact until perhaps another journey, another age. Thus, the comet stands revealed in our mind's eye, a relic of Genesis, a composite of fire and ice, memory and story. Ice as memory, dust as story. The comet brings both to us. As it travels closer to the sun, it sheds more of that material, as if slowly turning the pages of a very old book written in water and carbon. Each glimmer in its tail is a syllable from that book, telling of the time when the sun was young and the planets were only grains and clumps in a disk. And we, fortunate latecomers, get to witness this tale written in light across the sky. Now the comet is nearing its closest approach to the Sun. With each passing hour, it grows a bit brighter and its tails stretch a bit longer, responding to the intensifying solar energy. This is the climax of its transformation, from a quiet, frozen body to a dynamic celestial phenomenon. Soon it will round the Sun and begin its long voyage outward again. But what path does it follow exactly? How do these wanderers move through the solar system, and how long until this one might return? The next act in the comet's story is one of motion, an elegant dance on the strings of gravity with a tempo measured in centuries and millennia. The comet's journey is governed by celestial mechanics as precise as they are grand. This glowing visitor is not wandering aimlessly through the night. It is obeying the Sun, bound in an extended ellipse by the star's gravity. Most comets travel on elongated orbits that carry them from the deep freeze of the outer solar system into the warm inner regions and back out again. Some ellipses are so stretched that they are nearly open paths. The comet spends only a fleeting few weeks or months near the Sun and decades or centuries out in darkness. Our comet, too, is tracing such a path. Night after night, as you have observed, it shifts position among the stars, moving faster as it draws nearer to the Sun's embrace. It is like a prodigal child rushing through the inner solar system, swinging around the Sun, and then set to flee back to the outer darkness. Each comet's orbit has its own rhythm. Some, like the famed Halley's Comet, complete a circuit in roughly a human lifetime, appearing about once every 75 years or so, returning to our skies across the generations. Halley's Comet has been recorded since antiquity, each visit a bookmark in human history, connecting disparate eras with its periodic light. Many other comets have longer periods, hundreds, thousands, even millions of years, and some are on trajectories so expansive that they will never return at all. After one pass by the Sun, they are flung on escape paths into interstellar space, never to be seen again. Our current comet might be a long-period one. Perhaps it last visited when humans had just begun building cities, or perhaps it has never been here before at all, making its inaugural swing into the inner solar system since the time it formed. As the comet loops around the Sun at its closest approach, the moment called perihelion, it reaches its greatest velocity. The Sun's gravity pulls it into a swift slingshot. Then, as it recedes outward, it gradually decelerates, like a runner tiring on a long uphill climb. If we could trace its path from high above, we'd see a graceful elongated ellipse or perhaps a near parabolic arc, with the Sun offset from the center. The comet's motion is a kind of physical poetry, a dance governed by Kepler's laws of orbital motion, speeding up when near the Sun, slowing far away, sweeping out equal areas in equal times. In its motion, we can almost sense the ticking of a cosmic clock. Indeed, motion is time for a comet. For Halley's Comet, one orbit is roughly a human lifetime. For others, one orbit might outlast human civilizations. The orbital period of a comet becomes a measure of time on a scale far grander than our own. It reminds us that what seems a brief spectacle to us may be just one heartbeat in the comet's own centuries-long year. Now imagine the fate of our comet after this swing by the Sun. It will recede into darkness again, but not quite the same as it arrived. Every visit to the Sun transforms a comet a little. The heat vaporizes some of its ice, carrying away a portion of its mass. Sometimes the very shape of the nucleus may change, surfaces carved by jetting gas, cliffs collapsing as supportive ice beneath them dwindles, new fractures forming from thermal stress. A comet is not static. It's evolving with each passage. In a sense, these are living worlds in dormancy that awaken, shed material, and then return to slumber. Over many such cycles, a comet can drastically alter. Some comets, especially the ones on shorter orbits that pay frequent visits to the Sun, so-called periodic comets, gradually run out of the volatile ices that make them spectacular. Their once active surface may become covered in thick insulating dust, and the dramatic outgassing wanes. they become shadowed relics, dark, inert objects that masquerade as asteroids. Astronomers suspect that several near-Earth asteroids are actually extinct comets, comets that have shed their icy mantles and are now quiet, rocky bodies orbiting the sun without coma or tail. It's an intriguing life cycle, born in the distant cold, briefly flamboyant in youth and middle age when the sun's heat makes them grow comas and tails, and eventually settling into old age as a dormant, coal-black husk. Yet some comets meet far more dramatic fates. Not all survive their trip around the sun intact. Occasionally, a comet ventures too close to the sun, and the intense tidal forces and heat rip it apart. One famous example was Comet Ison in 2013, which swooped extremely close to the sun, so close that the solar furnace boiled it to destruction. Observers hoped to see it emerge from behind the sun as a dazzling object, but it disintegrated, leaving only a fading ghost of dust. There are also comets known as sun grazers that routinely dive near the sun. Many of them perish similarly, evaporated in a single fatal solar kiss. Comets can also break apart far from the sun. Sometimes internal pressures from heating, or perhaps a rotation that becomes too rapid due to jets acting like thrusters, cause the nucleus to fracture. In the mid-19th century, astronomers watched Biela's comet split in two. By the next few passes, the fragments had further crumbled and the comet eventually vanished. But it wasn't entirely gone. Years later, Earth's sky was lit by an unexpected meteor storm, the Andromedids, as our planet swept through a stream of debris that was once Biela's comet. The cosmic snowball had become a cloud of shooting stars. It was a striking lesson that comets and meteor showers are intimately linked. The dust that a comet leaves in its wake continues to orbit along the comet's path, and if Earth's orbit intersects that path, we are treated to a meteor shower. Every August, when we enjoy the Perseid meteors, we are actually witnessing the dusty legacy of Comet Swift-Tuttle. Each swift streak across the sky is a particle from that comet burning up as it plows through our atmosphere. In October, the Orionids are the remnants of Halley's Comet. Thus, even as a comet travels onward or disintegrates, it leaves behind a story in the form of meteors, a cosmic memory that can recur annually, like the echo of the comet's visit. Fragmentation can sometimes turn one comet into a family. The pieces of a shattered comet may themselves continue as smaller comets, at least for a time, each fragment developing its own coma and tail, if it still has enough ice. In the early 1990s, comet Shoemaker-Levy 9 was drawn too close to Jupiter and was torn into a chain of over 20 fragments by the planet's gravity. These fragments then, famously, plunged into Jupiter a year later, one after another, like a string of celestial firecrackers, in July 1994. Over several days, each fragment slammed into the giant planet, leaving enormous dark scars in Jupiter's cloud tops, some larger than Earth. It was a stark reminder of how fragile these cosmic ice balls are, and how violent the solar system can be. Even when a comet remains intact, it is in a continual dance with the sun's influence through the solar wind. Earlier we touched on how the solar wind shapes the ion tail, but the sun's breath can do more than shape. It can at times dramatically resculpt the tail. The ion tail is made of charged particles, so it responds to the solar wind's magnetic field. When a particularly strong gust of solar wind, or a coronal mass ejection, an eruption of plasma from the sun, blasts a comet, it can cause a phenomenon breathtaking to behold. The comet's plasma tail can be severed. Observers have seen a comet's tail detach and drift away into space like a loose ribbon when struck by a solar storm, only for a new tail to begin growing from the coma afterward. It's as if the sun momentarily snatched the comet's flowing hair, and the comet calmly grew it back once the solar tempest passed. Such events underline that the comet is not a static beam of light, but a dynamic structure constantly responding to the environment of space. The solar wind, invisible to our eyes, plays puppeteer with the glowing tails, sometimes twisting them into knots or causing them to kink and ripple, other times snapping them off entirely and forcing the comet to regrow its luminous train. All these transformations, sublimation, fragmentation,
disintegration, and interaction with the solar wind form the life cycle of a comet. They are born quietly in the darkness, flare to glorious life as they approach the sun, and eventually, one way or another, they fade. But in doing so, they deposit material into the inner solar system, scattering dust and gas that can have effects far beyond their brief visitation. Think of how meteor showers enrich our skies, or how comet dust adds a trickle of material to Earth's atmosphere each year. On rare occasions, something far larger than dust might strike Earth, linking a comet's fate directly with our own. Indeed, to fully grasp the significance of comets, we must explore not just their physical life cycle, but their influence on the cycles of planets and possibly life itself. For the story of comets is intertwined with the story of Earth. Long before there were eyes to marvel at comets, when Earth was a molten young planet, comets may have been raining down upon it. And long after we are gone, a comet could be the harbinger of great change on this planet once again. Comets give, and comets take away. They are agents of chaos and creation in equal measure. To see how, we look back into the deep past of our own world. Eons ago, in the chaotic infancy of the solar system, Earth was a barren, searing world, pummeled by constant impacts. It was a realm so hot that any water present at its birth would have boiled off or been baked into the rocks. And yet today, Earth is a water world, its surface mostly ocean, and it teems with life built from complex organic molecules. How did our once dry planet gain its life-giving water and carbon chemistry? Comets are central characters in one prevailing theory. In those primordial days, countless comets and asteroids were flung inward by the gravitational jostling of the newly formed giant planets. This period, known as the Late Heavy Bombardment, was a time of intense rain, of cosmic debris falling through the skies. Amid the storm of meteoroids and asteroids, many comets likely plunged toward the sun, some crossing Earth's orbit along the way. These icy interlopers smashed into the young Earth, releasing torrents of water and myriad organic compounds upon the surface. Each comet impact would have been catastrophic locally, but collectively, over millions of years, they may have delivered a substantial portion of Earth's oceans. Picture comet after comet vaporizing on impact, their water contributing to an atmosphere thick with steam, which eventually cooled and fell as rain to fill basins and carve out oceans. Along with water came organics, simple carbon molecules, maybe even amino acids, that had formed in the comet's ices or on dust grains within them. These were scattered like seeds upon the sterile early Earth. It's a hypothesis that has gained support from scientific detective work. By comparing the isotopic flavor of water, specifically the ratio of heavy hydrogen, deuterium, to normal hydrogen in comets and Earth's oceans, researchers seek clues to our water's origin. Some comets have water that is a close match to Earth's ocean water, suggesting they could indeed be contributors. Others have water that is heavier or alien in composition, which initially cast doubt on comets' role, pointing more to asteroids as the main water bearers. But then a pattern emerged. Certain comets known as hyperactive comets, which spew out more water than their surface area suggests because they expose fresh ice in outbursts, have water with an isotopic signature similar to Earth's. One famous example is Comet 103P Hartley 2, whose water was found to be much like Earth's. The thinking is that these hyperactive comets dredge up water from deep inside their nuclei, water that was protected from fractionation, the loss of lighter hydrogen, and retains an Earth-like fingerprint. If so, perhaps many comets hide Earth-like water in their interiors, only releasing it under certain conditions. The debate isn't fully settled, but it's increasingly plausible that a meaningful fraction of our oceans is cometary water. Beyond water, the delivery of organics might be even more crucial. Earth's nascent environment had to gather the raw materials for life,
and comets were like cosmic delivery trucks for complex carbon molecules. The discovery of amino acids in comet dust and of organic compounds like sugars and nucleobases in meteorites suggests that the basic toolkit for life's chemistry was readily available in space and likely rained down on the early Earth. It's a humbling thought. The carbon in your muscles, the nitrogen in your DNA, some of those atoms and molecules could have arrived in the fiery plunge of comets long ago. We are, in a very real sense, part comet. In those tumultuous early times, each fiery impact that delivered water also delivered destruction. But Earth eventually cooled, water pooled, and chemistry began to stir in those waters. Perhaps the organics from comets mixed with those from asteroids and from Earth's own atmosphere to form the soup of life's beginnings. Some scientists even speculate about comets not just seeding ingredients, but possibly ferrying actual microscopic life, though the survival of life through the trauma of space travel and impact seems very unlikely. More concretely, comets likely helped set the stage for life on Earth by providing the ingredients and maybe even triggering environments like impact-heated pools or hydrothermal systems, where those ingredients could assemble into self-replicating molecules. So the comets, which for so long were feared as omens of death, may have been in part bringers of life. It's a beautiful irony. The disastrous stars, as ancient people called them, from the Latin dis aster, bad star, possibly delivered the water we drink and the carbon frameworks on which our bodies are built. With each comet that we study, we learn more about this connection. The Rosetta mission's findings of complex organics and the presence of glycine in Comet 67P reinforce that comets carry many of life's building blocks. And just think, every meteor shower that sprinkles Earth is perhaps delivering a few more microscopic grains of exotic carbon or specks of prebiotic matter into our environment. The exchange between Earth and comets didn't end in the distant past. It continues at a slow drip even now. Looking up at our comet now, you might see it differently knowing this. It is no longer just a distant light. It is a relative of sorts, a visitor from the family that helped create our home's oceans and air. The emotional experience of seeing a comet, already intense, gains another layer: gratitude. Without such celestial wanderers, Earth might have remained a dry rock. There might have been no ocean voyages or clouds or rain, no life as we recognize it. The cosmos, by means of comets, may have nurtured the conditions for us to exist. Yet the relationship between comets and Earth is not solely nurturing. History shows it has also been occasionally catastrophic, and potentially could be again. The same impacts that brought water in the distant past could, in a later era, bring ruin. To understand that duality, consider not just the deep past, but events within human memory and scientific observation. Consider those famous comets that have intersected not with Earth directly, but with our understanding and fears. Let us recall some of the notable comets that have blazed into human history, shaping culture and science, and even one that collided with a planet in our own lifetime. They each have lessons to teach about both the promise and peril of these cosmic wanderers. Throughout the ages, a few comets have stood out so vividly that they earned a place in human memory and history. They became more than just celestial objects. They became characters in our cultural story. One such comet is Halley's Comet, arguably the most famous of all. It is a returning wanderer, revisiting the inner solar system roughly every human lifetime. This periodic nature, first confirmed by the astronomer Edmund Halley in the 18th century, means Halley's Comet has been observed again and again through recorded history. It has woven itself into the fabric of human events. In the 11th century, a bright comet, later identified as Halley, appeared over Europe. So astonished and fearful were people that they even embroidered it into the Bayeux tapestry, linking it to the Norman conquest of England. To them, it was a harbinger of great upheaval. A few centuries later, near the dawn of the 14th century, Halley's comet graced the heavens again. The Italian artist Giotto di Bondone, inspired by its appearance, painted a comet as the Star of Bethlehem in one of his frescoes. This is a rare instance of a comet being portrayed as a positive omen, a divine sign of hope. Halley's comet has often served as a convenient scapegoat for tragedy. Each time it returned, people searched their histories for disasters to blame on it. By the early 20th century, science had advanced, yet when Halley approached in 1910, public anxiety still ran high. Earth was due to pass through the comet's tail. Although astronomers knew the gases were too diffuse to harm us, sensational newspapers warned of poisons in the tail. Entrepreneurs sold comet pills and gas masks to a fearful public. When nothing dire occurred, humanity edged another step away from superstition. This same comet has also marked personal stories. Famed American writer Mark Twain was born under Halley's comet on one of its visits, and he predicted he would go out with it on its return. Indeed, he died the day after it reappeared decades later. Halley's comet, coming like clockwork roughly every 75 years, has become a symbol of continuity amid change. It has been recorded since at least 240 BC by Chinese astronomers. It was the comet of the Norman conquest, the comet of Twain, and it will be the comet of generations to come. When it returns in the mid-21st century, it will connect yet another chapter of human history to all those past. Each return of Halley's comet has taken it further from an omen and closer to an old friend, one that maybe, just maybe, helped inspire us to learn the laws of celestial motion. After all, Edmund Halley's bold prediction of its return was vindicated when it duly arrived on schedule in the mid-18th century, a triumph of reason over fear. Another comet that left a deep impression is Comet Hale-Bopp, the great comet of 1997. Hale-Bopp was discovered 2 years before its closest approach, which gave the world plenty of time to anticipate its performance. And perform it did. As it neared perihelion in 1997, Hale-Bopp became one of the brightest comets of the 20th century. It was visible to the naked eye for a record 18 months, an almost unheard of duration. Night after night, people could step outside and see its brilliant form hanging in the sky. It sported a dazzling white dust tail and a delicate blue ion tail, both clearly visible even from light-polluted cities. Under dark rural skies, Hale-Bopp was breathtaking, a luminous apparition with twin tails fanning out, one a broad curved sweep of pale gold, the other a straight ray of electric blue. Many who saw it still speak of it as the once-in-a-lifetime spectacle it was. Hale-Bopp became a media sensation, drawing millions of casual observers out to look upward. For the vast majority, Hale-Bopp was a source of joy and wonder. Families had comet-gazing picnics. Photographers took stunning images that adorned magazine covers. It reminded humanity that even in the late 20th century, with entertainment on screens and lights drowning out the stars, a natural celestial event could captivate the world. Sadly, there was a darker footnote. A cult called Heaven's Gate believed a spaceship was following the comet and committed mass suicide as Hale-Bopp peaked. A tragic reminder that even in modern times, comets can inspire dangerous fantasies in the unhinged. But for nearly everyone else, the comet was purely a wonder, not a portent of doom. It also provided scientists a prolonged opportunity to study a bright, active comet. Its great intrinsic brightness, partly due to an unusually large nucleus, tens of kilometers wide, and long duration, allowed detailed observations of its behavior, providing a wealth of data on cometary gas and dust dynamics. After 1997, Hale-Bopp receded toward the outer solar system. It won't return for over 2,500 years, but it left an enduring memory that will be recounted in astronomy books and by those who saw it. In more recent times, Comet Neowise, officially CE 2020 F3, became a household name. In July 2020, during a period of global isolation and anxiety, this unexpected visitor offered a celestial respite. discovered by a space telescope only a few months prior, Neowise survived its passage by the Sun and emerged into the Northern Hemisphere's evening skies as a striking object. For those who ventured out at dusk or before dawn, often from backyards or lonely country roads, Neowise displayed a graceful golden dust tail and a fainter ion tail. It wasn't as brilliant as Hale-Bopp had been, but it was the most impressive comet in decades, easily visible to the naked eye, especially under clear, dark skies. Photographs of Comet Neowise went viral. Images of a curving comet above city skylines, above quiet, pandemic-deserted streets, above mountain ranges and lakes. People across the Northern Hemisphere, many seeing a bright comet for the first time, found solace and even delight in its presence. For a few weeks, news feeds and social media were filled not just with earthly troubles, but with photos and exclamations about the comet. It felt like a gift from the universe in a troubled year, a reminder that beyond our immediate crises, there is still beauty and wonder. Neowise 2 is now departing on a long orbit, not to return for nearly 7 millennia. Its visit was fleeting but uplifting, a kind of cosmic encouragement at a time when humanity needed a bit of hope and perspective. Not all notable comets are remembered for gracing Earth's skies. Some are famous for their fate elsewhere. Comet Shoemaker-Levy 9 is one such comet, known not for a spectacle to human eyes, but for a dramatic cosmic collision. In 1993, astronomers Carolyn and Eugene Shoemaker and David Levy discovered a strange, squashed-looking comet near Jupiter. It turned out that this comet had been captured by Jupiter's gravity and torn into pieces. By 1994, those pieces, over 20 of them, were on a collision course with Jupiter. In July 1994, the world watched as, one after another, the chain of comet fragments slammed into Jupiter's southern hemisphere. Each impact released energy equivalent to many millions of nuclear bombs. Earth-based telescopes saw huge dark blotches appear on Jupiter's clouds, bruises the size of Earth itself, where plume after plume of debris rose and fell. This was the first time in history that humans directly witnessed a collision between two celestial bodies. The event riveted astronomers and the public alike. It was sobering. If such a fragment, a few kilometers across, had hit Earth, we would be looking at an extinction-level event. Thankfully, mighty Jupiter took the hit. In fact, Shoemaker-Levy 9's demise underscored Jupiter's role as a cosmic guardian. Its gravity often sweeps up comets that might otherwise menace the inner solar system. The comet's dramatic end gave planetary scientists an unprecedented look at an impact's effects and, in a sense, served as a wake-up call about cosmic impacts in our own neighborhood. It taught us that giant impacts are not just relics of the distant past. They can happen in real time, in our cosmic backyard. These four comets, Halley, Hale-Bopp, Neowise, Shoemaker-Levy 9, each tell a different tale. Halley connects us to history and the cyclical nature of time in the heavens. Hale-Bopp dazzled with its brilliance and longevity, uniting people in collective awe. Neowise arrived as a serendipitous gift during a dark time, a reminder of wonder beyond our immediate troubles. Shoemaker-Levy 9 dramatically illustrated the ongoing power of cosmic events and our need to pay attention to the skies not just for inspiration, but for safety. Through them, we see the many faces of comets, periodic and familiar, sudden and spectacular, gently inspirational, or violently instructive. They have been interpreted through the ages as omens or miracles, and now we interpret them as natural phenomena rich with information. In understanding these comets, we better understand the solar system and ourselves. For much of human history, comets were enigmatic, often feared. The sudden appearance of a comet, unpredictable and striking, shattered the normalcy of the night sky. To people who believed the heavens reflected divine will or signaled events on Earth, a comet's arrival was an intense portent. Ancient Chinese records called comets broom stars or guest stars, and linked them to the rise and fall of emperors. In Europe, comets were long viewed as the terror of kings. When a bright comet appeared, it was said to foretell the death of a ruler or a great disaster. The very word disaster comes from Latin roots meaning bad star, showing how deeply that fear was ingrained. Yet, as our understanding grew, the mythological gravity of comets began to fade, replaced by scientific gravity, Newton's gravity. In the late 16th century, the Danish astronomer Tycho Brahe observed a bright comet and noted that it showed no measurable parallax against the background stars. This meant the comet was farther than the moon, contradicting Aristotle's long-held idea that comets were mere atmospheric phenomena. Tycho's revelation placed comets in the celestial realm of planets and stars, subject to the same physical laws. Then Edmund Halley's prediction and the comet's return cemented the idea that comets follow regular orbits, not the caprice of gods. What used to inspire mass panic gradually came to inspire mass curiosity instead. Today, instead of fearing comets, we send spacecraft to meet them face to face. We seek to know them intimately. This transition from dread to curiosity is one of the triumphs of human intellect. But even now, knowing what they are, comets have lost none of their capacity to astonish. A great comet in the sky can still make even a jaded city dweller stop in their tracks and feel small and in awe. Perhaps we no longer see a fiery sword of the gods, but we do see a marvel of nature, and that is more than enough to stir the soul. In our modern quest to understand, we have embarked on a new chapter, sending robotic emissaries to chase comets down and unravel their secrets. The era of modern missions has brought comets within our reach and understanding like never before. In the mid-1980s, as Halley's Comet approached once more, humanity seized the opportunity to greet it with technology. In 1985, the European Space Agency launched Giotto, a spacecraft designed to fly by Halley's Comet during its 1986 visit. Giotto was a small, hardy probe equipped with cameras and instruments to sample the dust and gas around Halley's nucleus. No one knew exactly what would happen as it zoomed through the comet's coma. The risk to the spacecraft was high, like flying through a blizzard of grit at tens of kilometers per second. On the night of closest approach, in March 1986, Giotto hurtled past Halley's nucleus at about 600 kilometers distance. It was pummeled by dust. A grain even knocked its camera off alignment for a moment. But Giotto survived and sent back the first ever close-up images of a comet's heart. Those images were historic and mesmerizing. They revealed a dark, potato-shaped nucleus about 15 kilometers long, jetting brilliant streams of material into space from a few active regions. Only a small portion of Halley's black, carbon-crusted surface was actively venting gas. The rest remained dormant and oddly dark, reflecting only a few % of sunlight. Halley's Comet was not a translucent ghost, but a solid world, a very dark one, among the blackest objects in the solar system, wrapped in its self-made haze. Giotto's instruments also confirmed the richness of Halley's chemistry, detecting water vapor, carbon monoxide, methane, ammonia, and complex organic molecules. This encounter was humanity's first intimate meeting with a comet, and it transformed our picture of them. They were not fluffy, airy bodies, but solid, complex mini-worlds with varied terrain and ingredients. After Giotto's pioneering flyby, a bold idea took shape. Why not bring a piece of a comet back to Earth? That idea became reality with Stardust, a NASA mission launched in 1999. Stardust's target was Comet Wild 2, and its goal was audacious: fly through the comet's coma, catch particles streaming off the nucleus, and return them to Earth for detailed study. In January 2004, Stardust swooped within 240 kilometers of Wild 2's nucleus, exposing a tennis racket-shaped collector filled with aerogel, a lightweight, frothy material, to snare dust particles without vaporizing them. It also snapped pictures of Wild 2's nucleus, revealing a surface riddled with deep pits and spires, looking like a battered ice rock world with many vents. The flyby was harrowing. The spacecraft was hit by a spray of particles that caused it to wobble, but it stayed on course. In 2006, Stardust's sample capsule parachuted to a safe landing in the Utah desert. Inside was precious cargo, thousands of tiny comet dust grains, the first samples from beyond the moon ever returned to Earth. When scientists analyzed Stardust's catch, the results were thrilling. They found minerals that form at high temperatures, like olivine and other crystalline silicates, mixed among the expected ices and carbon compounds. This suggested that material from the inner solar system had somehow traveled outward to mix into comets forming at the fringe. They also definitively found glycine, a simple amino acid, in the samples, proving that such biologically relevant molecules form in comets and can survive eons in space. The comet dust had a large component of complex hydrocarbons as well, a sort of cosmic tar. The Stardust mission showed directly in the lab that comets harbor the raw ingredients that would have been useful to the origin of life on Earth. For the first time, humanity held in its hands pieces of a comet, pieces that smelled of ammonia and almonds, as scientists described the scent of the sample upon opening the canister, owing to trace organics. We were touching the very stuff that had probably helped seed our planet. While Stardust was still en route back to Earth, another daring mission was underway: Deep Impact. This 2005 NASA mission had the dramatic goal of punching a hole in a comet. The target was Comet Tempel 1. Deep Impact carried a 370-kilogram copper impactor, which it released directly into Tempel 1's path, while the main craft observed from a safe distance. On July 4, 2005, the impactor smashed into the comet's nucleus at over 10 km, excavating a crater and throwing up a huge plume of dust and gas. Telescopes on Earth and Deep Impact's mothership watched the flash and debris. The impact ejected subsurface material that hadn't been exposed to sunlight. Analysis of the ejector showed a lot of fine powdery dust, more than expected, and revealed the presence of carbonates and clays, minerals that form in liquid water within the comet. This was a surprise. Perhaps Tempel 1 had mild internal heating or water at some point to produce such minerals. The comet seemed to have a very fluffy, porous interior, so much so that the crater it created was larger and gentler, walls that collapsed inward, than anticipated. Deep Impact effectively did a controlled excavation of a comet and found that beneath a relatively solid crust was softer, perhaps more fragile material. It was our first comet geology experiment. Later, in 2011, another mission, Stardust Next, flew by Tempel 1 and imaged the Deep Impact crater, confirming it was about 150 meters across. Through Deep Impact, we learned not just composition, but also something about the structural strength and layering of a comet. It was like knocking on a door and hearing an unexpectedly hollow sound from within. If Giotto opened the door and Stardust and Deep Impact peered through, Rosetta moved in and stayed for a while. The European Space Agency's Rosetta mission, launched 2004, was breathtakingly ambitious: to rendezvous with a comet and accompany it for over 2 years, observing it up close as it approached the Sun and even landing a probe on its surface. After a 10-year journey, Rosetta arrived at Comet 67P Churyumov-Gerasimenko in mid-2014. The images it sent back of Comet 67P were astonishing. The nucleus was shaped like a rubber duck, 2 lobes connected by a narrow neck. This bilobed shape hinted that 67P might be the result of a gentle merger of 2 separate comets in the past. Rosetta entered orbit around 67P, mapping its surface in unprecedented detail. It revealed towering cliffs, pit-like depressions venting jets of vapor, fields of boulders, and smooth plains of dust drifts. This was not a simple, dirty snowball. It was a diverse little world with geological features and seasonal changes. In November 2014, Rosetta deployed its small lander, Philae, to attempt the first landing on a comet. Philae's harpoons failed to fire upon touching down, causing it to bounce twice. It finally came to rest in the shadow of a cliff. Though it didn't land perfectly, Philae still managed to conduct experiments during its initial battery life of about 60 hours. It drilled the surface, finding it surprisingly resistant beneath a softer crust, tasted the local vapors, detecting a bouquet of organic molecules, including some complex ones like nucleobased building blocks, and sent back panoramas from the comet's surface, an alien landscape of dark rocks and looming cliffs, lit by an eerie, faint sunlight. Philae's unexpected resting place meant its solar panels got little light, and it fell silent after a few days. But in those hours, it became the first human-made object to operate on a comet's surface, a truly historic achievement. Meanwhile, Rosetta continued orbiting and observing 67P from above. Over the next 2 years, it watched the comet come alive as it neared perihelion in August 2015. The frozen ground warmed and gushed out jets of gas carrying dust. Rosetta flew through these jets, measuring their composition. It sniffed a rich array of chemicals: water, carbon dioxide, carbon monoxide, methane, methanol, ammonia, hydrogen cyanide, formaldehyde, hydrogen sulfide. Hence the comet smelled of rotten eggs and urine, as scientists cheekily noted, and even molecules like glycine, the same amino acid stardust found, and phosphorus. It was a chemical treasure trove. One of the biggest surprises was the detection of significant amounts of molecular oxygen, O2, in the comet's halo. This was completely unexpected because O2 is highly reactive and was not thought to survive from the solar nebula. Its presence suggested that 67P's clathrate ices might have trapped oxygen during the comet's formation, or that some other process was generating it. This finding alone kept comet scientists busy with new theories. Rosetta mapped the comet's gravity and found the nucleus had a density much lower than water ice. It was roughly 50–60% empty space. This confirmed the extremely fluffy, porous nature of comet interiors. It also observed changes on the comet. Portions of cliffs collapsed, new jets opened up, boulders moved, likely from gas outbursts. We were witnessing geology on a comet, slow by human terms, but fast by geological terms, happening in real time. As the comet passed its closest approach to the Sun and headed out, activity subsided. Rosetta continued to follow it until, in September 2016, with its mission ending, Rosetta was gently guided to impact on the comet's surface, taking close-up images down to the final moments. It came to rest on the comet, effectively becoming one with it. Through Giotto, Stardust, Deep Impact, Rosetta, and other missions, like a brief flyby of Comet Borrelly by Deep Space One in 2001, or of Comet Hartley 2 by Epoxy in 2010, we have transformed comets from distant, fuzzy apparitions into tangible worlds that we can visit and even sample. We found that comet surfaces can be as hard as rock in places, and as soft as powder in others. We found organic chemicals of complexity beyond what many imagined. We confirmed that much of Earth's water could indeed have come from these ancient ice bearers. We learned that comets are diverse. Some might be built of two fused halves like 67P, others more single-bodied. Some are very chemically rich, others somewhat depleted, as Halley's comet turned out to have an unusual composition with lots of organics and a relative dearth of water. We've learned that their behavior is not random, but driven by solar heating. Yet each comet has its own personality, with different regions turning on at different times, often dependent on the shape and tilt of the comet. Yet despite all these advances, mysteries still cloak comets. In fact, each discovery seems to open new questions. Among the biggest is how exactly comets formed. We know they coalesced in the outer solar nebula. But was it a gentle coming together of icy grains sticking bit by bit, or a more abrupt collapse of a clump of material? Evidence from Rosetta's images of 67P's goosebumps, small meter-sized clumps on the surface, suggests comets might be aggregates of smaller building blocks, loose piles of pebbles that assembled under weak gravity. Their high porosity supports this idea of a gentle assembly, like a cosmic snowdrift. But we haven't witnessed it directly. It remains an active area of research, with some leaning towards the pebble accretion model, and others considering whether large instabilities in the protoplanetary disk caused kilometer-sized comets to condense rapidly. We also still wonder what lies beneath the surface of comets. Rosetta gave us hints. 67P had a very homogeneous interior in density and likely no large voids, but we don't know if comets have internal stratification, like layers from different eras of accretion, or if they are rubble piles through and through. We haven't yet drilled deeply into a comet. Filey tried a shallow drill. Are comets perhaps clumps of material loosely held, or do they have cores of different composition? The Deep Impact experiment gave a peek, suggesting softer interior under a crust, but one data point isn't enough. The chemistry of comets also holds puzzles. That oxygen on 67P is one. Another is why some comets have much more carbon monoxide than others. Comet Borisov, the interstellar visitor we'll discuss soon, had an unusually high CO content. Does that reflect its birthplace around a different kind of star, or did it form in an extremely cold part of its original system? Even within our solar system, comets show compositional variety. For instance, comets from the Oort cloud versus Jupiter family comets from the Kuiper belt display different ranges of water isotope ratios. We're not sure if that's due to where they formed or how often they've been heated by the sun. Then there's the conundrum of activity outbursts. Comet Holmes famously brightened by a factor of 1,000,000 in 2007, temporarily becoming visible to the naked eye as a new star in Perseus. This happened when it was far from the sun. What caused that eruption? Possibly an internal pocket of volatile ices suddenly venting, or a major fracture exposing fresh material. We still lack a predictive theory for such outbursts. And fragmentations. Why do some comets, like Comet Atlas in 2020, just fall apart spontaneously even before reaching perihelion? Were they rubble piles loosely held that spun up too fast? Or did heat create cracks that rapidly propagated? Each fragmentation event we catch, and we caught many smaller ones with Rosetta on 67P, teaches us a bit more, but it remains somewhat unpredictable. The line between asteroids and comets has blurred too. We've found bodies in the asteroid belt at much warmer, closer orbits that show comet-like activity, the so-called main belt comets, or active asteroids. These likely have reservoirs of ice that occasionally get exposed. Are they comets that migrated inward and became dormant until hit by something? Or asteroids that somehow held onto pockets of ice for billions of years? It's a mystery that challenges the neat comet-asteroid divide. Perhaps in the end, comet is a behavior outgassing more than a strict category, and some asteroids can behave like comets if given the chance. Just as we began to settle into our new understanding of comets, the cosmos threw us a curveball from beyond our solar system. In recent years, a thrilling new chapter in the story of comets began with the appearance of objects from other star systems. These interstellar visitors have expanded our perspective and raised intriguing questions. The first of these was spotted in late 2017, an object later named Oumuamua, Hawaiian for Scout. It was the first confirmed interstellar object passing through our solar system. But Oumuamua did not announce itself with a coma or tail. It appeared as a dot of light, like an asteroid. As astronomers tracked it, they realized it had come on a one-way hyperbolic trajectory from far beyond and was already outbound. Oddly, it showed no signs of outgassing. No fuzzy coma was detected despite sensitive searches. Yet, as more data came in, something strange appeared. Oumuamua's trajectory was deviating slightly from what pure gravity would dictate. It was as if a gentle force were pushing it, akin to cometary outgassing. If it was outgassing, it must have been doing so in a way we couldn't easily see, perhaps releasing molecules like hydrogen that don't produce visible glow, or perhaps only very small amounts. And then there was its shape, inferred from its changing brightness. It seemed to tumble end over end, with its brightness varying by a factor of 10. To cause such variations, Oumuamua must be very elongated or very flattened. Some models suggested it might be cigar-shaped, perhaps 400 meters long and only 40 meters wide. Others suggested a thin pancake shape. Either way, it was unlike any comet or asteroid we had seen. Some scientists humorously pondered if it was an alien probe, a notion largely dismissed by data, but a sign of how perplexing this object was. The leading natural explanations were that Oumuamua was a fragment of a larger body tidally shredded by a star, or that it was a dry comet, one whose volatiles had been mostly spent, leaving it with just enough gas to nudge it, but not enough to form a visible coma. Another hypothesis was that it was made of exotic ices, like solid hydrogen, that could sublime without leaving a detectable signature. To this day, Oumuamua remains an enigma, a visitor that came and went before we knew what to make of it. Then, in late 2019, a second interstellar traveler appeared, and this one was unmistakably a comet. Discovered by amateur astronomer Gennady Borisov, Comet 2I Borisov arrived with a visible coma and tail. This was essentially an interstellar comet presenting itself exactly as our homegrown comets do. Borisov was observed for months as it swept through the inner solar system. Spectra revealed it contained water vapor, cyanide, diatomic carbon, all typical comet gases. Photographs showed a pretty ion tail. If we hadn't known its trajectory, Borisov could easily be mistaken for an ordinary long-period comet. Yet this was material from another star's nursery visiting us. One noteworthy finding was that Comet Borisov had an unusually high ratio of carbon monoxide to water in its vapor, far higher than most solar system comets. This suggested it might have formed in a colder environment. Carbon monoxide ice is very volatile and usually abundant only in very cold comets. Perhaps Borisov originated around a red dwarf star, or in the outer reaches of a system colder than ours. Apart from that, it was reassuringly familiar, which in itself was profound. It means the processes that form comets around other stars produce broadly similar outcomes. The juxtaposition of Oumuamua and Borisov was fascinating. The first was interstellar and weird, perhaps a piece of a comet's rocky core or something completely unexpected. The second was interstellar and yet comfortingly recognizable as a comet. These two barely begin to hint at the diversity of objects wandering between the stars. Our solar system likely ejected trillions of small objects during its formation too. Some of those might have reached other stars. Likewise, some comets in our Oort cloud might be immigrants from other stars born in the Sun's birth cluster. Interstellar comets are messengers between planetary systems. The realization that interstellar objects pass through and that we can detect them has energized scientists. Plans are being drafted for future missions that could try to intercept an interstellar object if one is discovered on approach. It's challenging. These visitors move fast on unpredictable paths, but not impossible with enough advance notice and a fast rocket or even a solar sail. One day, we might directly sample a comet from another star, analyzing alien ices in our labs. What an extension of our senses that would be. From all this, one clear lesson emerges. Comets, whether local or interstellar, connect us with the broader universe. They carry clues of cosmic history and even hints of cosmic commonalities. They show that the ingredients and processes that shaped our solar system are not unique. They likely happen in countless systems. Comets have been agents of creation, possibly delivering life's ingredients, but as history and shoemaker Levy 9 remind us, they can also be agents of destruction. It is natural then to contemplate comets and extinction events. Could a comet end life on Earth or drastically alter our world? The idea has moved from folklore, blazing star means end of the world, to serious science. About 66 million years ago, a catastrophic impact triggered a mass extinction that ended the age of dinosaurs. A huge crater off Mexico marks that event. For a long time, it was assumed to be an asteroid impact.
due to certain mineral evidence in the debris layer. But some researchers have suggested it might have been a comet, specifically a fragment of a long-period comet flung in by Jupiter or the Sun's tidal forces. This hypothesis, while not mainstream, reminds us that comets can hit planets. If the Chicxulub impactor was indeed a comet, or a piece of one, then comets have literally reshaped the history of life on Earth. Even if it wasn't, comets surely have struck Earth over geological time, perhaps during epochs where the evidence has been eroded away or masked by other processes. Some scientists in the 1980s noticed a possible periodicity in mass extinctions and speculated that maybe every 26 million years, a shower of comets bombards the inner solar system, causing devastation. They even hypothesized a companion star named Nemesis, far out, whose orbit every 26 million years would disturb the Oort cloud. Nemesis has never been found, and the extinction periodicity is debated, but the notion of comet showers remains plausible. The Sun does bob up and down in the galactic plane, and encounters with passing stars happen from time to time. It's very conceivable that once every few tens of millions of years, the Oort cloud gets a gravitational kick, and a rain of long-period comets is sent inward. Most would miss Earth, but some might not, and even one large one could spell disaster. Thus, comets might be woven into the fabric of Earth's long-term biospheric ups and downs. On human timescales, fortunately, civilization-ending comet impacts are extremely rare, but smaller events remind us of the hazard. In June 1908, an object, likely a small comet or asteroid, perhaps 50 meters across, exploded above the Tunguska region of Siberia, flattening an immense area of forest. No crater was left. The body disintegrated in the air, which is one reason some speculated it was a comet. All ice and dust, no solid remnants. Whether comet or asteroid, the Tunguska event released energy comparable to a large nuclear bomb. Had it occurred over a city, it would have obliterated it. We now have observatories constantly scanning for near-Earth objects. We've catalogued thousands of asteroids that could come close, but a long-period comet could still surprise us. Typically, we might discover such a comet only months to a few years before it enters the inner solar system. That's not a lot of time to prepare if one were on a collision course. Thankfully, these long-period comets are far less common in the inner solar system than asteroids. But the uncertainty is higher. We can predict asteroid orbits decades ahead. A comet arriving fresh from the Oort cloud is an unwelcome wildcard, though one with low probability. We've already been developing defenses. In 2022, NASA's DART mission successfully tested nudging an asteroid's orbit by crashing a spacecraft into it. A similar method could work on a small comet if we had enough warning, though comets often travel faster and could be harder to hit precisely. Other ideas for a comet threat might include attempting to break it up, though that could make multiple dangerous pieces, or even using a standoff nuclear blast to vaporize or deflect it. These are measures of last resort. The preferred approach is early detection. See it coming far away, and then any needed deflection can be very small. This is where continued observation is key. The Vera Rubin Observatory, expected to begin full surveys soon, will scan the sky deeply and frequently, which should significantly improve our chances of spotting that proverbial comet on a collision course decades in advance, if one exists. Jupiter also stands as a protector. Its gravity slings many inbound comets out of harm's way, or even gobbles them up, as with Shoemaker-Levy 9. Still, we do not forget that what crashed into Jupiter in 1994 could just as easily have been aimed at Earth had the celestial dice rolled differently. Thus, comets sit at a profound junction of themes. They are bringers of both life and death. They connect the deep past with the present and future. They remind us of the fragility and also the resilience of life. After all, if comets did help start life on Earth, one could say we owe our existence to them. And if one day a comet threatens to extinguish life, it may be that life, in the form of human technology and ingenuity,
will thwart it. There is a grand poetic symmetry to that. Mindful of both the promise and threat of comets, we look to the future and consider what lies ahead in our relationship with these celestial nomads. Each new comet mission has answered questions and raised others, and there are many plans brewing for further exploration. One eagerly anticipated project is ESA's Comet Interceptor, planned for launch later this decade. This innovative mission will not target a specific known comet. Instead, it will wait in space, at Earth's Lagrange point L2, until a suitable new comet is discovered inbound, ideally a pristine, first-time visitor from the Oort cloud. Once such a target is found, Comet Interceptor will redeploy to meet it. The mission actually consists of 3 spacecraft, a main probe and 2 sub-probes. As they approach the comet, the sub-probes will detach and fly by the comet at different distances and angles, while the main craft passes more distantly. This will provide multi-point measurements of the comet's gas, dust, plasma environment, and close-up views of its nucleus from different sides simultaneously. If all goes well, we might get our first look at a truly untouched comet, one that has never been fried by the sun before. Comparing its composition to comets like Halley or 67P, which have been cooked on repeated orbits, will help reveal what changes solar heating causes and what the original nebula material was like.
Another tantalizing ambition is a comet sample return mission that brings back icy material, not just dust. Stardust brought dust and some very small volatile traces. But imagine returning to Earth with chunks of actual comet ice, kept frozen the whole way. Scientists could peer into that ice with microscopes, dissolve it and run it through analyzers, sniff its vapors in ultra-sensitive instruments. A direct interrogation of primordial material. One mission concept, called Caesar, has aimed to do just this with Comet 67P, and although not yet approved, the desire remains. There are formidable technical challenges, keeping a sample at cryogenic temperatures on the journey home, for instance. But the reward would be unparalleled. We could, for example, directly measure the ratios of noble gases in comet ice, which tell us about conditions of formation, or discover complex organics that don't survive being fragmented and heated in space. We might even find interstellar grains in the ice, tiny pre-solar minerals preserved within, that could be extracted and studied grain by grain. Even without returning samples, we have powerful new observatories to study comets from here. The James Webb Space Telescope, with its keen infrared vision, has already observed comets, detecting water and carbon dioxide, and even confirming the presence of water vapor around a main belt asteroid that turned out to be quietly comet-like. Webb can detect extremely faint outgassing at great distances, potentially catching comets beginning to awaken far from the sun. Meanwhile, the Vera Rubin Observatory will, once operational, systematically scan the entire visible sky every few nights at unprecedented depth. This means it will catch new comets, likely in the outer solar system, and track changes in brightness, or even detect splitting events. Rubin might give us early alerts for comets that could become great spectacles, or, as discussed, any that pose hazards. Future missions are also considering touch-and-go landings, hoppers, or rovers on comet surfaces. Philae gave a taste, but imagine a rover that could drive, or more likely hop in the low gravity, across a comet, studying variations, or drills that could go meters deep to bring up a core sample, like we do on Earth for ice records. Another idea is a cryogenic laboratory in space. Essentially, if returning to Earth with ice is too hard, one could have a spacecraft land on a comet, ingest some ice and dust, and perform detailed chemical analyses on site, transmitting the results. This would bypass the sample preservation issue, but let us examine volatiles in situ. And looking further ahead, one can dream of more novel interactions. Comets could even become resources for spacefaring humanity. They are rich in water and carbon compounds, the very materials needed for life support and fuel. Some futurists imagine capturing a small comet and nudging it into orbit around, say, Mars, to provide a water source for a colony. That's far-fetched with foreseeable technology, but not beyond the realm of long-term possibility. At the very least, learning how to extract water from a comet, perhaps by drilling a well and letting the sun's heat pump the water out as vapor, could be incredibly useful for future explorers. There's also something profoundly poetic in the idea of riding along with a comet. Some have suggested a comet hopper mission, a spacecraft that would essentially hitch a ride on a comet for an entire orbit, perhaps powering down during the frigid aphelion far out, then awakening as the comet comes sunward and directly witnessing the changes from the surface. Imagine a robotic observer clinging to a comet through the dark freeze of the outer solar system, and then holding on tight as jets erupt around it near the sun. It would be risky, but what an adventure. Essentially accompanying a comet on its journey as a human proxy. Our toolset for dealing with the threat side of comets will also improve. The more we learn about comet composition and structure, the better we can plan deflection missions. If we know a comet is mostly a loose rubble pile, a deflection might need a gentle nudge to push it whole, rather than something that might shatter it. If it has a sturdy core, maybe a harder shove is viable. The observations from DART's impact on an asteroid and Deep Impact on Temple 1 form early experiments in what might become a mature technology of planetary defense. It is comforting to know that whereas our ancestors could only cower from the wrath of the comet, we are moving toward being able to guard against it. As our missions grow bolder, so too does our philosophical perspective. We started by chasing comets for science. In doing so, we ended up chasing some very old questions as well. Where did we come from? Are we alone? Comets are involved in both. They carry clues of our origin and also distribute the seeds of life potentially between worlds. There's a hypothesis called lithopanspermia, that life can travel on rocks knocked off planets. Comets could facilitate that by transferring water and organics, or even capturing microbes in a glancing blow and carrying them elsewhere, though surviving the ejection and re-entry is an extreme long shot. Even if that never happened, the exchange of organics certainly did. Earth's early surface was likely enriched by cometary infall. The more we study comets, the more we realize they are threads in the grand tapestry of the solar system, threads that weave through the fabric of time and space, tying planets to the sun to the galaxy, the present to the deep past and future. They are not mere background actors, but have played pivotal roles in the story of Earth and possibly many Earths. Having journeyed with comets from deep time to the present and gazed toward their future, we find ourselves drawn into a reflective pause. What do these ancient wanderers truly mean to us, as thinking beings in the cosmos? It's time for a more philosophical reflection on comets, to ponder not just what they are, but what they symbolize and inspire. We have followed comets with our science and with our imagination. In doing so, we have perhaps come to know them better than our forebears did, yet they still evoke the same awe they always have. There is a sense that in understanding comets, we are understanding a part of ourselves as well, our origins and our place in the cosmos. Comets, in a profound sense, are time travelers. They carry memories of the solar system's birth. When we say poetically that a comet's ice is memory, we acknowledge that within each comet's frozen heart lies the unedited record of a time before Earth existed. It is as though the comet is a mindful ancient being, holding in its core the knowledge of where we come from. As it sublimates, that memory is released in the form of gas and dust, which we capture with instruments and translate into stories of creation. Thus, the dust is story. Each mote of dust from a comet is a chapter from the solar system's youth, whether it be a tale of a distant star that forged a grain of sand, or a tale of two planetesimals that gently merged. The comet's tail unfurls these tales across the sky, and we, with science as our language, strive to read them. Beyond the literal information they carry,
Comets stir something emotional and almost spiritual in us. The light is longing. The soft, otherworldly glow of a comet seems to reach across the vastness, stirring a sense of connection and yearning. Standing under a comet's glow, one can feel a tug at the heart, a longing for understanding and transcendence. Perhaps it is we who project that longing onto the comet, but it feels as if the comet itself is a cosmic messenger, reminding us of the broader universe, beckoning us to come and explore. That glowing tail is like an arrow pointing away from our small world, out to the great wide cosmos, awakening our desire to venture outward, or at least to send our thoughts far beyond the horizon. There is also deep symbolism in a comet's transience. A comet appears, captivates the world, and then fades away into darkness once more. It is a fleeting phenomenon, here for a few weeks or months, then gone for centuries or forever. This impermanence is a poignant mirror to our own mortal existence. We too blaze bright for a brief moment in cosmic time, and then are gone. Yet, like comets, perhaps we leave something of ourselves behind, a meteor shower of influence, a memory in others, just as comets leave trails of meteoric dust that continue to intersect Earth's orbit long after the comet has departed. In that way, comets can symbolize the legacy we leave. They also teach us to appreciate the here and now. Every appearance of a great comet is unique and precious, something to be seized. How many people through history lived their whole lives without seeing a brilliant comet? To see one is a privilege. Comets thus remind us of the importance of witnessing and appreciating rare wonders when they occur. Comets also have a way of humbling us while simultaneously elevating us. When a bright comet dominates the night, we are reminded how small Earth is and how minor our daily concerns are against the backdrop of the cosmos. This is humbling. Many who have watched a comet felt that we are tiny under the stars feeling. At the same time, think of what it means that we, tiny as we are, can comprehend what a comet is. Through intellect and ingenuity, we have plucked the mystery out of that streak of light and identified it as a visitor from the fringes of the sun's domain, perhaps carrying ingredients that built our very bodies. Knowing that elevates us. We are not cowering creatures making up fearful myths. We are active participants in the cosmic story, understanding and even embracing these celestial phenomena. It's often said that we are stardust, and comets drive that truth home. The water in our bodies, the carbon in our cells, some of that is literally from comets or the same primordial cloud that birthed comets. We are linked by chemistry to these objects, and by studying comets, we are, in a way, studying ourselves and our origin. There's a profound unity in that realization. Comets, humans, planets, nebulae. We are all made of the same atoms, all part of the same grand cycle of matter and energy. Comets dramatize that cycle, formed from the solar nebula, possibly contributing to planets, maybe ending as meteor showers falling back to a planet, a full circle. Comets also ignite imagination like few other natural phenomena. They have always done so. They appear as if by magic, change visibly from night to night, and vanish into memory. They provoke questions about the unknown. Even today, a child seeing a comet for the first time might feel the spark of curiosity that leads them to become a scientist, an artist, a storyteller. In that sense, comets are muse and mentor. They make us ask the big questions. What else is out there? Are we connected somehow to those distant wanderers? Could life travel on a comet? What would it be like to stand on one? Those questions have driven not only science fiction stories, but real scientific inquiry. From a philosophical viewpoint, one might say comets embody the concept of the cosmic journey. They spend most of their time in darkness, far from the sun, a long cold voyage, and then for a brief time they come into the light, flourish with a tail and coma, then plunge back into darkness. It's a cycle of exile and return, not unlike the mythic hero's journey in storytelling. The comet ventures from the unknown into the known, our visible sky, and back. In that,
Some see a metaphor for enlightenment. We too wander in darkness seeking the light of understanding, briefly gain it, and perhaps pass it on. There's also something communal about a great comet. When Neowise, or Hale-Bopp, or Halley appears, countless eyes around the world gaze at the same object. In a time where so much can divide humanity, a comet in the sky is a unifying sight. We all share one sky. Historically, unfortunately, that unity was often one of shared fear, but nowadays it can be one of shared wonder. That is no small thing. Awe is a powerful emotion that can bring people together, make them feel part of a larger whole. Comets continue to provide that experience. One can only imagine around a future campfire on Mars or a space station, colonists will point out a comet in the sky and feel that same ancestral awe and connection to each other. Finally, consider the perspective of a hypothetical cosmic narrator, a being or viewpoint as old as the stars, watching across time. Such a narrator might say, "Comets have been with you since before you knew how to speak. I have seen you fear them and adore them. I have seen you learn from them and even reach out to touch them. And through all this, the comets persist on their long orbits, indifferent but inspiring. Their gift to you is wonder, and what you have given in return is meaning." In other words, comets have no consciousness, but through us, they achieve a kind of narrative immortality. We have folded them into our story, scientific and cultural, thereby giving them a form of voice. In return, they have extended our senses and enriched our minds. Now the night deepens, and our comet, having shared so much, begins to slip away. It's time to step back into the shoes of that watcher under the night sky, you, me, any one of us, and experience a final quiet moment with the comet before it departs, taking with it everything we have learned and everything we feel, rolled into one luminous presence. The night is quiet again. Under the canopy of stars, a lone watcher stands, eyes turned heavenward. The comet that once blazed across the sky is now lower and fainter, its tail thinning into the darkness like the last wisps of a dream. The air is cool and still. There is a sense of peace, of contemplation, as the watcher keeps her gaze on that fading traveler. She reflects on what she has witnessed. In the course of this one comet's appearance, she has traveled in her mind from the birth of the solar system to the possibility of its death, from the ice in her own glass of water to the ice of interstellar space, from ancient myths to cutting-edge science. The comet, a smudge of light in the sky, has been a portal to all of that. The watcher feels small under the sprawling stars, yet oddly connected to them. The comet's long tail, now a mere delicate streamer, seemed to reach out and brush the vault of heaven. It is as if the comet drew a line between earth and sky, reminding her that the boundary is only in perception, not in reality. Earth and sky are part of one continuum, and she, standing here, is part of it too. She thinks of the comet's journey. It will soon slip beyond human sight, retreating into the outer solar system. Perhaps it will return centuries hence to other watchers, or perhaps this was its only pass near the sun, and it will roam the galaxy forevermore. In either case, she feels fortunate to have seen it. Generations before her lived and died under these stars without seeing such a comet. Generations after her may long for a sight as grand, but she was here, now, to witness this cosmic wonder. The thought fills her with gratitude and a gentle melancholy, like the bittersweet feeling at the end of a beautiful piece of music. The comet's tail now is barely discernible, an extension of darkness more than a beam of light. Dawn is approaching. A subtle lightening of the eastern sky tells her the sun will soon chase away the stars. The world around her, trees and hills, are beginning to emerge as silhouettes. The time of the comet is ending for this night, and indeed, for this apparition. She takes a deep breath of the cool night air, imprinting the scene in her memory. She knows that in all likelihood she will never see this particular comet again,
but its image will stay with her as long as she lives. In that way, the comet has become part of her. And through all she has learned and felt, she has, in a way, become part of the comet's story too. For a story is not just the teller, but the listener, and she has listened. In the silence, she offers a thought, perhaps a silent thank you to the comet for sharing its light, its ancient secrets, its beauty. Perhaps a goodbye, safe travels, until we meet again. If not in reality, then in the pages of a science book, or the canvas of a painting, or the strings of a violin piece composed in its honor. It's a quiet, private moment of communion between a human being and a celestial wanderer. Birds are starting to chirp. Morning's heralds. The stars are dimming. The comet is now all but lost in the brightening twilight. The watcher's vigil is over. She lowers her eyes to the horizon, where a faint blush announces the sun's imminent rise. There is a sense of completion, of harmony. The comet came, and now it goes, as has happened countless times through history. But this time, humanity understood it as never before. We rode along in our thoughts and even with our machines. We learned its composition. We passed its message. We made it ours in knowledge, even as it remains free in the sky. As the first golden arc of the sun peaks above the distant land, the watcher finally turns to head home. The comet has vanished into the morning glow, but she carries its imprint in her heart. She walks quietly, while behind her the sky grows day blue and Venus and the last stars wink out. She knows that somewhere up there, beyond the blue sky, the comet still sails away, now invisible, but real. Somewhere, far beyond the reach of her eyes, it continues on its path, a messenger heading back into the dark. It occurs to her that the comet will keep telling its story even as it leaves. To any world that intersects its trail of dust, perhaps a future spacecraft around Jupiter will sample it, or Mars's atmosphere will glean a mote. Its influence echoes even when it's gone. In the coming days, life will return to normal. The comet will become a memory shared by those who saw it, a tale to tell those who missed it. Perhaps some will feel changed by it, their perspectives broadened just a little. The watcher certainly does. As she reaches her doorstep, she pauses and looks at the brightening sky one more time. There is no trace of the comet, not even a speck, but she smiles because she knows it was there. She knows so much more about what it was and is, and yet the experience of it transcended the facts. In her mind's eye, the comet still glows, a phantom image that will stay with her. And she knows that in some sense, the comet will always be with us. Years hence, the meteors from its trail will streak through Earth's atmosphere, perhaps on some August or October night, and people will marvel at those shooting stars without realizing they owe their brilliance to this departed comet. The sky remembers, even if we humans might forget. And there will be other comets. She knows she might not see another great one in her lifetime, though she hopes she will. But certainly, others will come for future generations. Comets are part of the cosmos's ongoing story, one that will continue as long as the solar system exists and humans have eyes to look upward. Each comet is different. Each generation sees new ones. But there is a continuity too, the sense of awe they inspire. The sun is now fully above the horizon, casting its first rays on dew-laden grass. The watcher opens her door and steps inside, the warm interior welcoming after the long night. As she closes the door, she whispers a final goodbye to the comet. A goodbye that is really a until next time, whenever and wherever that may be. Outside, the sun's light floods the sky, washing away the stars of night. But though the comet has vanished from sight, it lingers in mind and memory, a gentle ghost that will long inspire stories, science, and dreams. The dark sky was pierced by a comet, sudden, bright, ancient. Its light may be gone, but the wonder it evoked in the watcher in all of us, remains, a glowing ember in the human spirit. And as long as that wonder endures, the comet story is not over. It will return again, in books, in songs, in the sparkle of a child's eyes, learning about the cosmos, and perhaps one day in the sky once more, to amaze a future world. The cosmic story continues, and we, the watchers, will always be ready to look up and greet the next celestial wanderer with curiosity and awe. Silence. In the beginning, there is nothing but the deep dark of space, cold, still, primordial. Then motion, a subtle stirring in the void. Out beyond the known planets, a distant glimmer emerges from darkness. An icy fragment, left over from the solar system's birth, has been jostled from its slumber. A comet is coming to life. It is ancient and newborn all at once. A time traveler from the dawn of creation, a survivor of billions of years, a frozen relic of our origin story. Each appearance of such a wanderer is a return and a reminder, as if the cosmos itself has memories to share. The comet begins its long fall toward the inner sun, carrying with it the secrets of a beginning. It was there at our solar system's first breath, and now, after ages of quiet, it moves again. Far from the sun, at the very edge of our solar system, lies the comet's birthplace, a vast unseen halo of icy bodies encircling the sun like a ghostly sphere. Here in the Oort cloud, trillions of frozen fragments drift in a great cosmic shell, so distant that the sun is merely another star in the sky. This is a realm of deep freeze, where comets spend most of their lives in exile. Temperatures hover just a few degrees above absolute zero, cold enough to preserve primitive ices for eons. In this dark sanctuary, time moves slowly. The comets are effectively in suspended animation, pristine and unchanged since the solar system was young. They carry water, methane, ammonia, carbon compounds, the ingredients of planets and life, locked in an icy matrix, safe from the sun's heat. Each one is a fragment of our origin, a piece of the protoplanetary disk cast outwards long ago and kept on ice. For millions upon millions of years, these cosmic snowballs circle invisibly at the solar system's frontier, like embers frozen in ash, waiting for a chance to glow again. What can trigger such a slumbering comet to awaken? Often, it is the gentle but inexorable tug of gravity, a disturbance from outside or within that nudges the comet onto a new path. Perhaps a distant star passes near the sun, and its gravity ever so slightly perturbs the orbits in the Oort cloud. The Milky Way itself exerts a tidal force, a gravitational rhythm that can slowly shake comets loose from their moorings. It has been said that up to 9 out of 10 long-period comets that visit us may owe their journeys to the subtle tide of our galaxy. Over immense spans of time, these influences add up. A comet that once traced a quiet, circular path, a light year from the sun, finds its course changed ever so slightly, enough that it begins to drift inward. Sometimes the trigger is sudden. A passing star like Schultz's star brushes through the outer cloud, as happened some 70,000 years ago, dislodging comets in its wake. Or, in the distant future, another star will plow through the Oort cloud in a few million years, sending a rain of comets sunward. Even the giant planets can play a role for comets that dwell in closer reservoirs. A gravitational nudge from Jupiter or Saturn can redirect a comet from the Kuiper belt or inner Oort disk onto a new, plunging trajectory. And so, by fate or chance, one frozen body is knocked off course. It begins a long fall, pulled inward by the sun's gravity after an eternity in the cold. The silence of the outer dark is broken. The comet has embarked on a voyage that will transform it utterly. At first, as the comet journeys through the outer reaches,
nothing visible happens. It is still too far from the sun, an unseen traveler in the interplanetary night. But slowly, inexorably, the solar warmth grows. The great journey may take millions of years from the comet's perspective, arcing slowly from the black outskirts toward the faint glow of the inner sun. As it crosses the orbit of Neptune and Uranus, the comet remains essentially a dark, icy nucleus, perhaps a few kilometers across, still cloaked in vacuum. But already, the sun's influence is mounting. The most volatile substances in the comet, gases like carbon monoxide and carbon dioxide, which turn to vapor at very low temperatures, begin to sublimate off the surface while the comet is still far from the sun. Even out near Jupiter's orbit or beyond, a large comet can wake up in subtle ways. Comet Hale, BOP, one of the brightest comets in modern times, was detected venting jets of carbon monoxide when it was further from the sun than Saturn, a ghostly breath in the frigid dark. Such outgassing is almost imperceptible to the naked eye, a faint haze around the nucleus, but it heralds the beginning of a comet's transformation. As the comet draws closer to the inner solar system, the sun's rays grow stronger and the pace of change quickens. Crossing the orbit of Jupiter and heading toward Mars' domain, the comet warms enough for water ice, its primary ingredient, to sublimate. What was once a solid, frozen mass now begins to unleash vapor. Jets of gas burst from beneath the surface, where sunlight heats pockets of ice, carrying with them clouds of dust particles that had been embedded in the ice. A tenuous atmosphere forms around the comet's nucleus. We call this the coma, a glowing halo of gas and dust that envelops the tiny nucleus like a luminous shroud. At first, the coma is thin and small, but as the comet approaches the inner solar system, the coma can expand to enormous size, often tens of thousands of kilometers across, dwarfing the nucleus that spawned it. Around some comets, a vast, invisible cloud of hydrogen gas also blooms, a halo that can be millions of kilometers wide. The traveler that was once a dark, icy rock has become something entirely different, a bright, active comet, announcing itself with a growing cocoon of vapor and dust. Now the sun's influence truly takes hold, sculpting the material blowing off the comet into dramatic structures that sweep across space. Solar radiation, the steady stream of light and energy from the sun, presses upon the dust in the coma, and the smallest particles begin to be pushed outward, away from the sun. At the same time, the sun's wind, a flow of charged particles streaming out at hundreds of kilometers per second, catches the gases of the coma and drags them into a long plume. The result is magical. One coma, but two distinct tails unfurling behind the racing comet. A dust tail blossoms, formed of fine grains of comet dust, reflecting sunlight. It often appears broad and gently curved, a pale fan that can stretch millions of kilometers and often has a yellow-white hue to our eyes. This dust tail traces the comet's trajectory like a painter's stroke across the stars, curving because the dust grains, having mass, lag behind the comet's head and continue along the comet's orbit, even as sunlight slowly shoves them aside. The other, more ethereal filament is the ion tail, made of gases, carbon monoxide, carbon dioxide, nitrogen, water vapor, that have been ionized by ultraviolet sunlight. These ions glow faintly, often in a blue or bluish-green hue, and being charged, they respond to the sun's magnetic field carried by the solar wind. The ion tail shoots straight away from the sun, a narrow, sword-like beam that can extend for tens of millions of kilometers, directly opposite the sun, regardless of which way the comet itself is moving. If you could hover in space, you would see the ion tail always pointing away from our star, sometimes leading the comet when it departs the sun, sometimes trailing it as it approaches, but always oriented by that invisible solar breeze. The comet now is fully awake, a cosmic apparition with a glowing head and trailing tails, hurtling faster and faster
as it draws near the sun's embrace. Its anatomy is laid bare in this moment of brilliance. At its core lies the nucleus, the heart of the comet. A small, dark body, typically only a few kilometers across, made of ice, rock, and complex molecules. A comet's nucleus is often an irregular, potato-shaped lump, far smaller than a city, yet it holds within it the potential to create spectacles spanning the sky. One might expect such an ice-rich body to shine brightly, but comet nuclei are surprisingly dark, blacker than coal, coated with dust and carbon, rich material. Indeed, a typical nucleus reflects only a few % of the sunlight that hits it. Scientists have found the surfaces of comet nuclei to be among the darkest materials in the solar system, likely because as ices sublimate away, they leave behind a crust of organic, rich dust. This dusty blanket absorbs sunlight, causing pockets of subsurface ice to heat and erupt in jets, the very process feeding the coma and tails. Surrounding the nucleus is the coma, a diffuse cloud of gas and dust grains that glows as sunlight scatters through it. To an observer on Earth, the coma often appears as a fuzzy, star-like core at the head of the comet. In fact, the word comet comes from ancient Greek kometes, meaning long-haired star, inspired by that misty head and trailing hair, like tail. From within the coma extend the two great tails, the broad, curving dust tail, glimmering with reflected sunlight, and the straight, often bluish ion tail, shining by fluorescing gases. The ion tail, being made of charged particles, is subject to magnetic whims. Ripples in the solar wind can cause it to kink or even detach. At times, astronomers have watched a comet's ion tail get ripped away by a particularly strong solar gust, only for a new tail to grow in its place as the comet continues to shed gas. These disconnection events are vivid reminders that a comet's graceful form is shaped by an ongoing interaction with our tempestuous sun. Dust tail and ion tail together turn the once invisible nucleus into a spectacle that can span half the sky. A comet at peak activity is like a giant paintbrush streaking away from the sun, its nucleus the handle, its coma the brush head, its twin tails the strokes of color on the canvas of night. What gives a comet's coma and tails their glow is not just sunlight, but the very substance of the comet itself, a rich chemistry that links these wandering ice balls to the origin of life. As the ices in the nucleus vaporize, they release not only water, but a menagerie of molecules that had been frozen inside. In that diffuse coma, scientists have detected some of the fundamental chemical building blocks that predate biology. There is water, H2O, the same simple molecule that fills Earth's oceans. There is carbon dioxide and carbon monoxide, the same gases that can shroud a planet's sky. Ammonia, methane, molecular nitrogen, simple compounds that carry the essential elements of life, stream away from the warming nucleus. Traces of more complex and sometimes toxic gases appear too. Hydrogen cyanide and cyanogen are commonly detected, which in ages past led fearful observers to imagine comets poisoning the Earth. Organic molecules form a substantial part of the outpouring. Formaldehyde, methanol, and other carbon-bearing molecules are common in cometary vapor. Perhaps most intriguingly, comets have been found to contain amino acids, the building blocks of proteins. In 2006, scientists studying samples from Comet Wild 2 discovered glycine, the simplest amino acid, embedded in the comet's dust. It was the first time an amino acid was confirmed in a comet, a discovery suggesting that these objects carry some of life's raw ingredients and can disperse them through space. Comet 67P, Churyumov, Gerasimenko, visited by the Rosetta spacecraft, provided a similar revelation. Rosetta's lander sniffed a suite of organic compounds on 67P's surface, including amino acids and phosphorus, key elements for DNA and cell membranes. It is a profound thought that a comet's brilliant tail, so beautiful to the eye, is in fact laden with the stuff of life's chemistry. Each shimmering trail is like the ghost of an ancient chemistry experiment, dispersing water and carbon across the heavens. This realization has led scientists to hypothesize that comets may have played a pivotal role in Earth's own story. Our planet formed dry and hot, likely unable to retain water in its early years due to intense heat. So where did Earth's vast oceans come from? One idea is that comets, rich in water ice, rained down on the early Earth, delivering water that pooled into seas. Along with water, they could have brought organic molecules, giving a boost to the prebiotic soup from which life emerged. Indeed, comets are time capsules from the birth of the solar system, preserving the kinds of materials that would have been present when Earth was young. Perhaps it was cometary impacts that seeded our infant planet with the volatiles and carbon compounds it needed to become a living world. This is the impact hypothesis for life's origins, that the violent delivery of cometary material was also a gift. Water for oceans, carbon for organic chemistry, maybe even complex organics that jump, started life's emergence. As poetic as it sounds, it finds some support in evidence. Certain comets contain water with isotopic ratios similar to Earth's oceans, implying a common source. A notable example was Comet 103P Hartley 2, whose water was found to closely match Earth's in composition, hinting that at least some comets could have contributed to our seas. However, not all comets fit the bill. Rosetta's measurements at Comet 67P showed its water was significantly heavier, suggesting that particular comet did not stock Earth's reservoirs. The debate continues, with current thinking pointing to a combination of sources delivering Earth's water. But beyond water, the notion that comets fertilized the early Earth with organic molecules remains compelling. Experiments show that amino acids can indeed form in comet, like ices under cosmic radiation, and comets have clearly shown they carry such molecules. Comets, in this light, are both harbingers and gardeners, capable of sowing life's ingredients, even as they portend destruction. Destruction is the other edge of that cosmic sword. The same impact deliveries that might have nurtured life can also wreak havoc. Comets have slammed into planets many times. We have a front row view of such a catastrophe from July 1994, when Comet Shoemaker, Levy 9, collided with Jupiter. This comet had been torn into fragments by Jupiter's gravity, and one by one, its pieces smashed into the gas giant, each impact releasing energy equivalent to millions of nuclear bombs. Earth-based telescopes watched in awe as fireballs erupted on Jupiter, and dark scars, larger than Earth in diameter, marred Jupiter's cloud tops. Those bruises on Jupiter were an eerie reminder. If such a comet were to strike Earth, the consequences would be apocalyptic. Indeed, some scientists speculate that a comet impact may have caused upheavals on our planet in the past. The mass extinction that ended the dinosaurs 66 million years ago is usually attributed to an asteroid, but it is conceivable a long-period comet could also cause such an event. In more recent geological history, there are hints, albeit controversial, that a sudden climate downturn 13,000 years ago might have been triggered by fragments of a disintegrating comet striking or air bursting over Earth. Whether or not comets can be definitively tied to past extinctions, they surely have the power to cause them. Even a small comet, only a kilometer or two across, hitting Earth would release more energy than all the world's nuclear weapons combined. The notion is terrifying precisely because comets often arrive with little warning. Unlike the asteroids we are mapping and tracking, a long-period comet from the Oort cloud can appear in our skies with only a few months or a few years' notice. It hurtles in at enormous speed, perhaps 50 or 70 kilometers per second relative to Earth, much faster than a typical near-Earth asteroid. That high velocity
means an impact carries tremendous kinetic energy. And as comets approach the Sun, they can also unpredictably brighten or fragment, complicating efforts to gauge their size and trajectory. All this makes them challenging targets for any hypothetical planetary defense. A sneaky, long-period comet might be detected only a short time before a potential impact, leaving us scant time to prepare. It's a cosmic game of chance that humanity must take seriously. So while we marvel at comets, astronomers also keep a wary eye on them. Surveys scan the sky for new comets, and space agencies contemplate how we might deflect or evacuate if one were ever found on a collision course. The menace is low, probability. Impacts by large, long-period comets are extremely rare on human timescales, but the potential consequence is high. Comets, then, embody the duality of nature, creators and destroyers, preservers of life's ingredients, yet capable of mass extinction. They remind us that our planet's story is intertwined with the capricious theater of space. One world's gentle rain of water may be another world's cataclysm. As we look up at a comet's beauty, we cannot forget the danger in its halo. And yet, in these icy visitors, we also see archives of the earliest history of our solar system. Each comet is a celestial archivist, preserving in its frigid nucleus a record of conditions from over 4.5 billion years ago. Locked away in that dark, porous ice are tiny grains of dust, older than Earth, some perhaps older than the Sun, solar grains from ancient stars. The composition of comets, the ratios of isotopes in their water, the mix of organic molecules, the presence of noble gases, all carry information about the environment and processes that prevailed when planets were forming. When we study a comet, we are in a sense reading a memoir of the solar system's youth. Comets have been called time capsules by scientists, and rightly so. Untouched by geologic activity or intense solar heat, a comet's nucleus can preserve volatile compounds that would long ago have disappeared from planets. For instance, the detection of molecular oxygen streaming from comet 67P was a great surprise. O2 is so reactive that it's rarely found in space except as a byproduct of life. Yet Rosetta found abundant O2 in 67P's coma. The discovery suggested that the oxygen was primordial, trapped in the comet since the solar system formed, and only now being released. Thus, comets can carry unexpected relics of the chemistry of the protoplanetary nebula. Similarly, the mix of minerals in comet dust has astonished scientists. Samples from Comet Wild 2 contained not just the expected ices and interstellar dust, but also minerals that form at extremely high temperatures, like olivine and CAIs, materials typical of the inner solar system near the early Sun. Their presence in a comet that formed far out beyond Neptune implies a grand radial mixing occurred in the early disk. The infant Sun's ferocious winds or jets must have blown these fire, forged grains outward, or perhaps turbulence stirred the pot, embedding a bit of sun. Fire in bodies born in the icy cold. Each comet analyzed gives us another piece of the puzzle of planetary formation. Clues to how water was distributed, how organic molecules evolved, how quickly the Sun's materials mixed. It is as if the comets are libraries, each carrying a few pages of a very old book. By reading enough of them, we can reconstruct chapters of our own origins. This is why space agencies have made comets prime targets of exploration. Within their dust and ice are chapters of our cosmic history, waiting to be read. In the past few decades, humanity has reached out to these celestial archives with robotic emissaries, ushering in a golden age of modern comet exploration. No longer content to observe from afar, we have sent spacecraft to chase comets down, land on them, even pluck samples and return them to Earth. Each mission has revealed unprecedented wonders, peeling back layers of mystery. In 1986, when Comet Halley last visited, a fleet of probes swept by Halley's nucleus, capturing the first close-up images of a comet's heart.
Those grainy photos astonished scientists. Halley's nucleus was a dark peanut-shaped rock, about 15 kilometers long, jetting out fountains of gas and dust. It confirmed the basic model of a dirty snowball, as astronomer Fred Whipple had poetically described comets. Fast forward to the new millennium, and our ambitions grew. In 2005, NASA's Deep Impact mission performed a bold experiment on Comet Tempel 1. It shot a 370-pound kg copper impactor into the onrushing comet, while the main spacecraft observed from a safe distance. On July 4, 2005, the impactor struck Tempel 1 at over 10 km/s, blasting out a brilliant explosion of material, a brilliant flash of light, as mission scientists described it, that later analysis showed was sunlight glinting off the plume of ice and dust flung from the comet's surface. For the first time, we had literally cracked open a comet to see what lies beneath its crust. The results from Deep Impact were revelatory. The impact kicked up fine powdery material, indicating that Tempel 1's interior is not solid rock or ice, but more like talcum powder or freshly fallen snow. A very fluffy structure, weaker than a bank of powdery snow. In fact, scientists concluded the comet might be 50th and 75% empty space inside, its ices and dust forming a loosely bound sponge. The plume analysis also detected a burst of organic compounds and carbon-rich dust. A huge increase of carbon containing materials was seen in the ejecta, showing that the comet's interior holds a substantial amount of organic matter. And within the dust, telescopes found microscopic clay and carbonate minerals, substances that form in liquid water, raising the puzzling possibility that liquid water had existed transiently inside or on Tempel 1. Deep Impact thus painted a picture of a comet as a fragile amalgam of primitive dust and ice, laden with organic molecules and even complex compounds, largely unaltered since the early solar system, except for a thin surface crust. It reinforced the idea that comets could have delivered organics to Earth by demonstrating the richness of organics beneath the surface. The mission also dramatically visualized how comets are eroded by each encounter with the Sun. One of the mission's key findings was that Tempel 1's interior ices, a well shielded from sunlight by a layer of dust, meaning the deep interior could still harbor pristine ices from billions of years ago. Deep Impact's feat was not just scientific, but cinematic. Humanity punching a cosmic snowball to reveal its secrets, and it succeeded beyond expectation, confirming that much of a comet's story lies hidden just beneath a dusty veneer. Where Deep Impact blew a hole in a comet, NASA's Stardust mission delicately gathered pieces of one and brought them back to Earth. Launched in 1999, Stardust chased Comet Wild 2 and in 2004 flew through its coma, using an ingenious catcher made of aerogel to snag particles from the comet's tail. The spacecraft then turned around and delivered these particles to Earth in 2006, the first time we ever retrieved macroscopic samples from a comet. When scientists opened Stardust's sample canister, they found tiny scorched tracks in the aerogel, each made by a high-speed comet dust grain embedding itself. At the ends of some tracks, they found intact particles, giving us a direct, tangible piece of a comet to analyze in labs. The analysis was full of surprises. Wild 2's dust was a chemical kaleidoscope, abundant silicate minerals like olivine and pyroxene, mixed with truly primitive interstellar grains that predate the solar system. The comet was like a bag of trail mix, combining ingredients from all over the solar system. Most importantly, Stardust samples had a diverse suite of organic compounds, including a variety of carbon-based molecules, some akin to those seen in meteorites, but others unique. In 2009 came the dramatic announcement that glycine was positively identified in Stardust's return samples. It was the first direct proof of an amino acid in a comet. The first time an amino acid had been found in a comet, NASA noted, supporting the theory that some of life's ingredients were formed in space and delivered to Earth. The glycine in Weil-2 was likely formed by non-biological processes in the ice of the protosolar nebula, or even earlier in interstellar clouds. Yet here it was, preserved in a comet, and now in a dish on Earth. Stardust also found that Weil-2's makeup challenges the old simplistic notion that comets formed solely in the outer reaches. It suggested significant mixing of material across the young solar system. In essence, what Stardust brought back was a message in a bottle from 4.5 billion years ago, telling us that the nursery of the planets was a dynamic place where fiery and frosty materials commingled, and that comets carried an inventory of compounds relevant to both planetary geology and biochemistry. The success of Stardust was so great that the mission was extended to fly by Tempel 1 in 2011, interestingly, allowing us to see the crater that Deep Impact's impactor had made, and to observe how the surface had changed after one additional orbit around the Sun. Through Stardust, a literal piece of a comet lives in our laboratories, continuing to be studied with ever more advanced techniques and likely to yield insights for decades. It is as close as we've come to holding a comet's heart in our hands. Perhaps the most ambitious comet rendezvous was the European Space Agency's Rosetta mission. Launched in 2004, Rosetta spent 10 years cruising through space before softly catching up to Comet 67P Churyumov-Gerasimenko in 2014. When Rosetta arrived, 67P was still far from the Sun, a relatively inactive nucleus, which allowed the spacecraft to do something unprecedented: enter orbit around the comet. For over 2 years, Rosetta flew alongside 67P, observing it in exquisite detail as it warmed through perihelion and then cooled again. Rosetta became like a companion to the comet, a robotic witness to its entire cycle of awakening and slumber. The images it returned were breathtaking. 67P's nucleus was revealed as a bizarre rubber duck-shaped object with cliffs, plains, and towering jets spurting from pits. We saw the surface up close: cracked terrains, big boulders precariously balanced, and smooth dust covered basins. It was clear that even a small comet has a complex geological landscape, shaped by eons of sublimation and perhaps even episodes of fragmentation and re-merging. Rosetta's orbit sometimes brought it within a few kilometers of the surface, where it could practically taste the coma. Its instruments detected a veritable chemistry set around the comet. Not only the expected water, CO2, CO, but also molecular oxygen as mentioned, and a zoo of organics, acetylene, formaldehyde, methanol, and even more complex ones like amino acids and polyols. One of Rosetta's major findings was that 67P's water had a DH ratio 3 times that of Earth's oceans, casting doubt on the idea that comets like it brought most of Earth's water. But conversely, its detection of abundant organics and even phosphorus showed that comets are rich in life's ingredients. Rosetta also carried a small lander, Philae, which in November 2014 was released to land on 67P's surface, the first landing on a comet nucleus. In a dramatic series of events, Philae bounced and came to rest in a shadowed nook. In its short active time, Philae still managed to drill and sniff the comet's surface chemistry, detecting complex organic molecules, including 4 compounds never before detected on a comet, such as acetone and propionaldehyde. Though its battery died after a few days, Philae had already given us the first ground truth of a comet's surface, confirming it was a mixture of hard ice and dust with organics, and measuring its hardness and composition locally. Meanwhile, Rosetta kept orbiting and tracking changes, watching jets switch on, measuring how much mass the comet lost at perihelion, and then, as the comet receded from the Sun, observing the activity ebb. In September 2016, as 67P journeyed back outward, Rosetta gently descended to the comet's surface and joined it, a controlled landing that ended the mission. The wealth of data Rosetta returned has been transformational. we learned that cometary activity can create sinkholes and pits as subsurface ice pockets sublimate. We saw the day-night cycle of the comet driving regular water vapor pulses. Perhaps one of the most surprising Rosetta findings was the detection of large amounts of molecular oxygen, an unexpected guest, suggesting that 67P's ices formed in an environment that trapped O2, or that some reaction was producing O2 on the comet. Rosetta truly made 67P one of the most studied comets in history, turning it from a fuzzy dot in telescopes into a tangible world with its own character. By riding along with a comet, Rosetta fulfilled an old dream: to understand, from up close, how a comet lives and changes. It's as if for 2 years we had a seat on the comet's shoulder, watching it breathe and evolve. Rosetta's legacy is profound, not only in its scientific discoveries, but in cementing the idea that these icy wanderers are accessible places that we can explore directly, even land upon, as we would a moon or an asteroid. Just when we thought we had seen it all, nature delivered a completely unanticipated twist: comets from beyond our solar system. In 2017, astronomers detected a faint object on a hyperbolic path, meaning it was not bound to the sun, screaming through the inner solar system. Dubbed Oumuamua, it was the first confirmed interstellar object ever observed in our solar system. Unlike the comets we know, Oumuamua showed no visible coma or tail. It was more like a mysterious spindle. Its brightness fluctuated dramatically, suggesting an elongated or flat shape tumbling end over end. It passed closest to the sun and then headed out, exiting just as fast as it came. Only later did scientists realize it had a slight non-gravitational acceleration, as if something gave it an extra push. We got only a brief glimpse of Oumuamua, and it left more questions than answers. Was it a comet that had lost most of its volatiles? A shard of a shattered planetesimal from another star? A bizarre iceberg of pure hydrogen or nitrogen ice that outgassed invisibly? Its nature remains debated, an enduring mystery streaking between the stars. Then, in 2019, a second interstellar visitor was spotted, this time behaving much more like a normal comet. 2I Borisov, discovered by amateur astronomer Gennady Borisov, came in on a high-speed hyperbolic trajectory. Unlike Oumuamua, Borisov sported a palpable coma and tail. It was clearly an icy comet from another star, shedding gas and dust as it neared our sun. Astronomers were ecstatic. Here was a bona fide interstellar comet that we could study with our telescopes for months. And study it they did. Observations revealed that while Borisov looked similar to comets from our solar system, its composition had intriguing differences. In particular, Borisov was enriched in carbon monoxide. It had significantly more CO relative to water than any solar system comet observed at similar distance. CO is very volatile, sublimating at very low temperatures, so such a high concentration hinted that Borisov formed in an extremely cold environment, perhaps in the outer reaches of its home system around a cool, red dwarf star. One study even suggested Borisov might be a fragment from a Pluto-like dwarf planet orbiting another star, ejected during some collision event. Aside from CO, Borisov's makeup implied that chemically it wasn't entirely alien. It reinforced that the basic processes that make comets around other stars produce objects akin to those we know. Yet the differences, like the CO excess, are valuable clues to the diversity of planetary systems. As one astronomer remarked, an interstellar comet is like having a sample of another star's protoplanetary disk delivered to us. Borisov streaked through and was gone by 2020, but during its visit, we effectively had an emissary from an unknown solar system in our own backyard. These interstellar comets have broadened our perspective immensely. They confirm that small bodies roam interstellar space, likely ejected during the formation of planetary systems. They hint that the phenomena we observe in our comets, outgassing organic chemistry, are common in the galaxy,
occurring around distant stars as well. Who knows what other exotic compositions or forms interstellar comets might have? We caught only 2. Statistics suggest there are countless more drifting between the stars, and we've just gained the capability to detect them. These alien messengers ignite our imagination. One day we might even send a probe to intercept one, to truly sample material from another star. For now, we use our best telescopes, like Hubble and ALMA, to glean what we can as they pass. In the silent rush of Borisov and Oumuamua, we felt the cosmic connection of distant worlds. They made the interstellar void just a bit more intimate, showing that nature flings pieces of worlds across the gulfs of space. A comet from a star 100 light years away might end up lighting our sky for a brief moment, a reminder that the story of comets is a galactic story, not just a solar system one.
What does the future hold for comet science? It is an exciting time, for our tools and plans are evolving rapidly. Soon, an era of powerful survey telescopes will dramatically increase the discovery rate of new comets. The Vera C. Rubin Observatory in Chile, set to begin full operations in the mid-2020s, will scan the entire sky nightly with a huge camera. It's expected to find thousands of new comets, including many faint, distant ones that were previously missed. By one estimate, Rubin's 10th-year survey could quintuple the number of known objects in the solar system, effectively illuminating the population of distant long-period comets and maybe even catching incoming comets years before they reach the inner solar system. This means earlier warnings for any potential threats and more time to prepare missions to particularly interesting comets. Rubin might even catch the next interstellar visitor on its way in. Meanwhile, specialized spacecraft are on the horizon to meet comets on their own terms. The European Space Agency is developing Comet Interceptor, a mission scheduled for launch in 2029. Unlike previous missions that targeted known periodic comets, Comet Interceptor will wait at the Sun-Earth L2 point for a suitable target to appear. The idea is to be ready to ambush a truly new comet, ideally one making its first ever approach from the Oort cloud, or even an interstellar comet like Borisov. When such a pristine comet is discovered inbound, Comet Interceptor's trio of probes will deploy and fly by it, imaging it and sampling its environment in detail. This mission concept embraces the unpredictability of comets, essentially saying, we'll be ready when the cosmic dice roll a good one. On the sample, return front, scientists are eager to build on Stardust's success by bringing back a larger, more pristine sample of a comet, including volatile ices. A proposal called Caesar was developed to revisit Comet 67P and collect at least 100 grams of material, carefully isolating the volatiles so that even the sublimation gases could be returned in a sealed container. Though not yet funded, Caesar or similar concepts remain high on the wish list because having a well-preserved chunk of a comet's nucleus in terrestrial labs could revolutionize our understanding of comet chemistry. We would be able to analyze amino acids for chirality, search for complex organics, and perhaps even prebiotic compounds with the full power of modern analytical chemistry, and precisely date grain components to see if some predate the solar system. Future mission planners also dream of landing on a comet again, this time with rovers or hoppers that could explore multiple sites, or even drilling into a comet to bring up samples from a meter or two down. Technologically, this is challenging. Comet surfaces are low, gravity, uneven, and active, but not impossible. There's also talk of missions to special comets like Main, belt comets. In fact, the James Webb Space Telescope recently detected water vapor from a Main belt comet, confirming that water ice can survive in that region. With Webb's keen infrared eyes, astronomers can now study the outgassing of comets in unprecedented detail, even when the comets are far from Earth or faint. Webb and its successors will examine the molecular makeup of comet comas, detecting trace species and isotopes that ground telescopes struggle to see. All these developments Better surveys, agile interception missions, advanced sample returns, and powerful space telescopes are converging to ensure that the next decades will be a renaissance in cometary science. We stand to answer some burning questions. How do comet nuclei structurally differ? What precise recipes of organic chemistry do they carry? And could those have led to life's emergence on Earth? How do comet populations in other star systems compare to ours? Are there many Borisovs out there with exotic compositions? Are there detectable patterns in comet orbits that hint at undiscovered distant planets? Each new comet observed or visited is another data point in unraveling these mysteries. Even as we peer ahead, comets remind us of the cyclical nature of time and the grace of celestial mechanics. Some comets are periodic. They return on regular schedules, their orbits bound to the sun in ellipses like cosmic clockwork. Halley's Comet, for instance, completes an orbit about every 76 years, faithfully revisiting the inner solar system as generations of humans pass. It is a periodic comet of the Halley type class, meaning its path is elongated and inclined, taking it far beyond Neptune before swinging back around. Halley has been observed since antiquity. Each return, it has been noted by those who knew to expect it, or feared it as an unpredictable omen in older times. It will return again in 2061, completing yet another cycle in its millennia, spanning journey. Many other comets belong to Jupiter's family, like Comet Encke, which whips around the Sun every 3.3 years, the shortest orbit of any known comet. Encke's frequent returns make it a familiar, if modest, comet. Its orbit is tightly bound near the inner planets, likely shaped by past interactions with Jupiter that captured it into a smaller loop. On the other extreme are long, period comets, those that take thousands or millions of years to return, or may be visiting the inner solar system for the first and last time, if their orbit is open. These come screaming in from the Oort cloud with orbital periods so long, they effectively appear just once from humanity's perspective. Some long-period comets might be on bound orbits of, say, 100,000 years, but others, after slinging around the Sun, get flung out entirely, either by gaining energy from a planetary encounter or by having come in on a trajectory that wasn't bound in the first place. In a sense, each comet's fate is written by gravity, by the immutable equations of orbital dynamics and the chance encounters it experiences. A periodic comet, like Encke, found a stable niche and will likely keep cycling until it gradually evaporates away or a perturbation kicks it out. A comet, like C 2012S1, was likely a first-time visitor from the Oort cloud. It dived near the Sun and disintegrated, its fragments carried off on hyperbolic escape paths, never to return. The cycles can also evolve. A long-period comet might be captured into a shorter period by a lucky interaction with Jupiter, or a periodic comet might get tossed out by a similar encounter. One famous example, Comet Brooks 2 in 1886, had a close brush with Jupiter that radically changed its orbit, essentially capturing it into a new, shorter period. Conversely, Lexell's comet in 1770 passed extremely close to Earth, and then, after 2 apparitions, passed near Jupiter and was ejected from the inner solar system entirely, never seen again. Gravity giveth and gravity taketh away. Over time, periodic comets also evolve physically. Each passage by the Sun costs them some mass, like a spoon of ice cream melting off with each lick of heat. Eventually, many periodic comets likely fizzle out or break apart. Halley's Comet, for example, has been losing mass for thousands of orbits. Scientists estimate its nucleus has eroded considerably and may survive only another few thousand revolutions before it becomes an inert husk or vanishes in a spray of debris. In a sense, comets have life cycles, a birth, a long dormancy, a potential series of active apparitions, and a death either by evaporation, disintegration, or collision. Some comets die spectacularly, like Comet Shoemaker, Levy 9 did by impact, or like Comet Ison, which evaporated in the sun's corona, while others simply fade to black, their volatiles exhausted, so they no longer grow comas, but persist as dark, rocky objects akin to asteroids. It's thought that a number of near-Earth asteroids might actually be extinct comet nuclei, the remains of comets that died after many orbits of activity. For example, asteroid 14827 Hypnos and others show characteristics hinting they could be spent comets. Even Encke's comet itself has much lower activity than one would expect for its size, suggesting it's nearing exhaustion, shedding less material each pass. The torrid meteor showers that grace our skies every year in late October and early November are attributed to debris from Comet Encke's gradual decay. This meteor stream contains not just dust, but possibly larger fragments. Indeed, there's speculation that some Tunguska-sized objects in the torrid swarm are leftover pieces of Encke's parent body, hinting that Encke may be the remnant of a much larger comet that fragmented ages ago. All these patterns, capture, loss, fragmentation, periodicity, illustrate that comets, for all their wandering, follow the rhythms set by gravity. In their paths, we see the fingerprints of planets and forces that have shepherded them. Each comet's orbit is a story of where it came from and what it encountered. Some are near, parabolic, whispering of origins in the dark Oort cloud. Some are tightly elliptical in the plane of the ecliptic, betraying a past in the Kuiper belt or scattered disk. Some, like Halley, have retrograde or inclined orbits, suggesting they were tossed in from the Oort cloud, yet bound to return. Each path is an archive of gravitational interactions. It's humbling that even such seemingly erratic travelers obey the same physical laws that guide planets in their courses. The difference is that comets have 1 foot in Newton's clockwork and 1 foot in chaos. Their fates can pivot with a chance encounter. Thus, they symbolize both the predictability and the caprice of the cosmos. Through all these scientific lenses, however, a comet is more than just a subject of study. For those who stand under a clear night sky and witness a great comet arcing overhead, there is an undeniable emotional and philosophical impact. Comets have forever been omens and inspiration, provoking fear and wonder in equal measure. In ancient times, they were often seen as divine messages, the harbingers of doom, as many cultures called them. Their sudden appearance, unpredictability, and striking form set them apart from the regular stars and planets, which moved in reassuring order. To people who didn't know where comets came from, it was natural to imagine they were sent by gods or spirits. One culture might see in the comet's tail the flowing hair of a weeping woman, a celestial mourner heralding sorrow. Another might see a fiery sword blazing across the heavens, an unmistakable sign of war and wrath from the gods. The ancient Chinese called comets broom stars and long-tailed pheasant stars, and painstakingly recorded their appearances and how their tails pointed, interpreting them as portents of imperial fortunes. A comet, seen in 1066, was recorded in the Anglo-Saxon Chronicle as a fearsome sign. Indeed, that year saw the Battle of Hastings, and the famous Bayeux tapestry depicts the comet with people staring and pointing, captioned Isti mirant stellum. These men marvel at the star, which they believed heralded the fall of King Harold and the rise of William the Conqueror. Across cultures, the word disaster literally means bad star, from Latin dis, astrum, reflecting the belief that an ill-omened star brought calamity. Even as late as 1910, when Halley's comet returned, despite humanity's strides in understanding, a wave of public fear swept through because spectroscopes found toxic cyanogen gas in the comet's tail, and newspapers sensationally claimed Earth would be poisoned as we passed through it. People bought gas masks and anti-comet pills in panic, though scientists reassured that the gas was far too rarefied to have any effect.
Comets have thus been mirrors for human emotions, fear of the unknown, the need to find meaning in the unpredictable. But they have also been viewed with awe and curiosity. Not all cometary omens were negative. Some ancient societies saw them as heralds of change that could be positive or at least significant. And in the Renaissance, as understanding grew, comets became objects of fascination for early scientists like Tycho Brahe and later Newton and Halley. The transition from superstition to science in comet study is one of the triumphs of human intellect. Yet even now, knowing what they are, we can still feel the mythic resonance when we see one. There is something poetic about a glowing traveler appearing unannounced, silently traversing the night, and then disappearing into the dark again. We can empathize with our ancestors. A bright comet in ancient skies must have felt like a rupture in the normal order of things, a moment when heaven's script flipped to a new page. Even today, a great comet can unite global audiences in shared wonder. In 1997, Comet Hale, Bop hung in the sky for months, so bright it was visible even above cities. It became a cultural phenomenon in a quiet, uplifting way. Millions of people, regardless of nationality or belief, gazed up at its jewel tails night after night, reminded that we all share the same sky. Comets thus have a unifying quality too. They prompt us to look upward and outward, to ponder our place in the universe. They are emblems of impermanence and renewal. Each comet's apparition is fleeting on the human scale, a matter of days or weeks of peak display. Yet the comet itself endures on a much longer orbital cycle, or if not, its materials disperse and perhaps seed new worlds. Watching a comet, one senses the slow ticking of cosmic time. The comet may have last visited before we were born and will return long after we are gone. In that realization is a humbling truth. Our lives are brief, and these celestial events link generations separated by centuries. A person in ancient China who noted a comet on a bamboo chronicle, a medieval monk who painted a comet in the margins of a manuscript, a modern child who makes a wish under a comet's tail, all connected by these passing cosmic hikers that journey between the ages. There's also a gentle existential lesson: fragility. The comet's beauty is born of its disintegration. It must lose itself to become the vision we adore. As it sheds those tails, it is gradually consumed. Nothing in this universe, not even a lovely comet, lasts forever. Halley's Comet, blazing through history, is slowly dying with each passage, its mass whittled away. One day, it will be gone. But new comets will take its place, falling in from the reservoir at the solar system's edge. Thus, comets embody the cycle of death and rebirth on a cosmic scale. They hint that creation and destruction are partners. The water that comets spend into space might become part of a new planet's ocean. The organics they scatter could seed fledgling life elsewhere. A comet's life and death are part of a grander continuum of matter. For those given to reflection, seeing a comet can feel like touching the infinite and the ephemeral at once. Its glowing form against the starry background speaks of beauty, unearthly, unowned, freely given, and of transience, because you know it will not last. Perhaps this is why comets have inspired so much art, poetry, and even religion. They provoke wonder about the workings of the heavens and introspection about our own lives. Mark Twain, who was born under Halley's Comet in 1835, famously mused that he expected to go out with it in 1910, and indeed, he died one day after Halley's perihelion that year. He saw the comet as a cosmic bookmark to his life, a personal omen in a scientific age. Such is the hold a comet can have on the human psyche. Now, the comet we have been following has looped around the sun. Surviving its blistering approach, it is outbound once more, its tails fading as the icy fountains weaken. We imagine ourselves riding with it briefly as it recedes.
the sun grows smaller. The great gaseous trails that made it magnificent are dissipating into space, left behind as a transient trace of its journey. Before long, the coma will collapse back onto the surface. The comet will become a quiet, solid traveler again. It returns to the cold depths, carrying perhaps a thin mantle of fresh dust from its recent activity, slightly altered but still essentially the same nucleus forged eons ago. In the skies of Earth, the once splendid comet is now barely a smudge in telescopes, then not even that. To the naked eye, it is gone. The show is over, the cosmic stage empty once more. But the memory remains, in photographs, in data, and in the minds of those who looked up and felt a connection with something beyond the ordinary. The night after a bright comet disappears feels a little emptier, as if a friend has departed on a long voyage. Yet there is also a sense of gratitude and privilege at having witnessed one of nature's most sublime performances. The sky returns to darkness and silence. Stars wheel in their eternal courses. All seems as it was. But we know that somewhere out there, far beyond our sight, that comet continues its journey. Perhaps it will circle back decades or millennia hence. Or perhaps it will wander interstellar space forever. And we know too that elsewhere, other comets are inbound, unseen as yet. The great vault of the Oort cloud still holds countless icy nomads awaiting their call. The Kuiper belt at the fringe of Neptune's realm steadily feeds short-period comets inward. Even now, dozens of comets traverse the solar system in various stages of their lives, most faint and unnoticed except by astronomers. The cosmos is never truly still. There is always motion, always a story unfolding, often out of sight. Under a moonless night, an observer on Earth gazes at the horizon where a comet once glowed. Now there is darkness. But that darkness is not empty. It is filled with possibility. The observer might recall how just weeks ago, a brilliant tail stretched there and feel a poignant longing. Comets remind us of how rare and precious some sights are, how we must cherish them when they arrive. They also remind us of the vastness of time. We may wait a lifetime to see a great comet, or we might be lucky to see several. It is not for us to command, only to appreciate. And in waiting, we participate in an age, old human experience, sky-watching with hope and humility. In the stillness of the pre-dawn hours, the world turns and a new day's light creeps in. The comet's memory melds into the growing glow of sunrise. Yet, somewhere, a comet moves. Perhaps it's our comet of focus, now far away, retreating into solitude with a dwindling tail still gently pushed by the solar wind. Perhaps it's another, just now beginning to feel the first whispers of the sun and growing a tenuous halo in reply. The cycle continues unbroken. One day, another distant glimmer will appear in our telescopes, another celestial visitor announcing itself in the silent language of reflected sunlight. And humanity will aim its curious eyes and instruments at it, studying it, admiring it, wondering about it. The horizon is never truly empty. It is an endless watchtower for the next marvel to rise. In the final meditation of this journey, we return to the image of a lone comet sailing through space. Envision it in the darkness. A tiny nucleus of ice and dust, perhaps peppered with rocky bits, with a faint aura around it. The last vestige of its coma gradually dispersing. It is quiet now, after the frenetic activity near the sun. It has shed material, but it has also gained something intangible. Another chapter in its existence, another imprint on the universe. Ahead of it lies a long arc into the outer solar system. Decades, centuries, or millennia from now, it may reach its farthest point and begin falling inward all over again, or it may escape to the stars, never to return. But at this moment, as it moves away from the sun, there is peace. The comet is alone with its ancient memories.
The stars around it are the same that shone when it first formed. The sun, now distant, gently pulls it along a precise path defined by gravity and momentum. A path that is part of the grand design of our solar system. We on Earth continue about our lives, but that comet and others like it persist on the margins of our awareness. They are like the background music of the solar system, usually quiet, occasionally swelling into a crescendo that demands attention. Knowing they are there enriches our view of the cosmos. For beyond the planets and their moons, beyond the asteroid belts and rings, there is this community of nomads that connect the solar system's fringes to its heart. They remind us that the solar system is not static. It has interchange and traffic, a circulation of material. They are messengers carrying water and organics from one realm to another. They are storytellers that can speak of the past and perhaps carry messages to the future. The sky tonight holds no obvious comet, yet someone with a telescope might find a faint one in Cancer or Hydra, a small fuzzy patch that is the only hint of an ongoing miracle. The rest of us wait until the next bright one graces us, and when it does, we will once again stand under the night, perhaps on a cool evening or crisp morning, and watch a silver, blue, or golden tail etched against the stars. We will feel the ancient stirrings that comets evoke, a mix of wonder, a touch of worry, a deep curiosity. We will perhaps whisper to a friend or child, "Look, a comet," joining our voice to a lineage of sky watchers going back to the dawn of our species. The comet will silently arc onward, impervious to our awe, yet somehow giving meaning to it. In the quiet, after the comet's passing, we understand something fundamental. We are part of a universe of cycles and journeys. Our own existence, so brief and small against the cosmic scale, is nonetheless connected to these grand events. The water in our bodies may have been delivered by a comet billions of years ago. The carbon in our DNA could be the very carbon that spent time in a comet's nucleus before becoming part of Earth. We observe the comet externally, but internally, we resonate with it, perhaps because we carry a bit of that stardust within us. The comets, in their peregrinations, illustrate the concept of cosmic impermanence and renewal. Things change, yet some patterns endure. They perish, yet from their remnants new structures can form. In that way, nothing is truly lost, only transformed. The horizon brightens further, dawn is near. Our imaginary comet friend is now far beyond human sight, but we know it moves on. The stars fade one by one as sunlight paints the sky. The earth spins toward day, and life goes on under the blue vault, largely oblivious to the celestial dramas overhead. But when dusk comes again and stars peek out, who knows? Perhaps a new visitor will have appeared. We live in expectancy and hope for such moments. Comets have been and will be with us for as long as humanity can look up. They are a bridge between the finite and the infinite, a reminder that while we are tiny, we are also part of something vast and beautiful. In the stillness after the celestial spectacle, one can almost hear the echo of what the comet has whispered. Remember me. Remember this feeling. We are all part of the same story. The sky is quiet now, but beyond the edge of sight, in the great dark between the stars, a spark of ice and dust continues on its way, carrying a tale as old as the solar system, headed for destinations unknown. It moves through the shadow with silent purpose, a wanderer forever. And somewhere, sometime, when the moment is right, it, or one like it, will return, igniting the night once more with its fleeting glory, and the cycle of wonder will begin again. Each ending is a new beginning in the story of comets. The horizon waits. Somewhere, a comet moves.